Hello there and welcome to Physics with William. Where curiosity gets comfortable, everyday objects become surprisingly interesting, and science takes its time explaining why the floor does not simply slide away beneath your feet. Tonight, we are looking at something that is working around you almost constantly. It is there when you walk across a room, when you hold a warm mug, when a bicycle slows down, when a match is struck, and when a stubborn jar lid refuses to cooperate. It helps your shoes grip the ground, keeps furniture where you left it, and allows your hands to pick things up without everything slipping through your fingers. That something is friction. Friction seems simple at first. Two surfaces touch, one tries to move, and something resists. We often picture rough surfaces catching against each other like tiny rows of teeth. It is a useful picture, but it is not the whole story. In fact, when scientists look closely at where friction really comes from, the answer becomes much stranger and much more interesting. The surfaces around us may look smooth, but at very small scales they are covered with bumps, valleys, ridges, loose particles, and irregular patches. Even polished metal, clear glass, and the glossy screen of a phone are not truly flat. When two objects touch, they do not meet evenly across their entire visible area. They make contact at scattered microscopic points, and those points carry nearly all the pressure between them. At those tiny meeting places, atoms come close enough to interact. Electrical forces act between them. Small regions may cling together for a moment. Softer material may bend. Harder bumps may press into weaker surfaces. Some contact points stretch, break, reform, and break again as motion begins. The steady resistance we call friction is the combined result of all this microscopic activity. Before we settle into it, I would love to know where you are listening from tonight. Perhaps you're in bed with the lights low, sitting beside a quiet window, or trying to relax while someone in another room is moving a chair across the floor with remarkable determination. You might also notice what you're touching right now: a blanket, a pillow, a chair, a phone, or perhaps a cup that is relying on friction to remain safely in your hand. It is worth noticing because friction is so familiar that we usually ignore it. We pay attention only when there is too much of it or too little. A rusty hinge attracts notice because it will not move easily. An icy pavement demands attention because it offers almost no grip. Most of the time, friction quietly remains somewhere in the middle, doing its work without asking for applause. If you find this kind of gentle exploration soothing, interesting, or simply helpful at the end of a long day, you can leave a like and subscribe to the channel. It helps this calm corner of physics reach other listeners who may also enjoy learning why ordinary things behave the way they do. There is no need to move quickly. Friction certainly will not. Now, let us begin with a very ordinary step. Imagine standing on a smooth kitchen floor. You lift one foot, place it slightly ahead, and push backward against the ground. Your body moves forward. This feels so natural that it rarely seems to require an explanation. Yet without friction, the backward push of your foot would not send you forward. Your shoe would simply slide behind you. Walking depends on a grip that forms before your foot begins to slip. The sole pushes against the floor, and the floor pushes back. Friction provides the sideways force that allows your body to accelerate. It does not merely slow motion. In this case, friction creates the movement you wanted. This is one of the first useful surprises. Friction is often described as a force that opposes motion, but that phrase can be misleading. Friction opposes sliding, or the tendency to slide between surfaces. Sometimes that resistance slows an object. Sometimes it helps an object move. A car accelerates because its tires push backward on the road, while friction from the road pushes the car forward. A person climbs because friction prevents hands and feet from slipping. A rolling wheel can use friction to gain speed without rubbing across the road. So friction is not simply the universe applying a brake. It is more like a strict agreement between touching surfaces. They may move together, but they resist moving across each other. The same agreement helps you hold a glass. Your fingers press inward against its sides. Gravity pulls the glass downward. Friction acts upward along the contact between your skin and the surface, preventing the glass from falling. Press more firmly, and you can usually hold a heavier object. The greater pressure creates stronger contact at the microscopic meeting points. More of the surface irregularities are pushed together, and the forces between the materials become more effective. This is why you tighten your grip when carrying something valuable, although sometimes the object is merely a biscuit and the sense of danger may be slightly exaggerated. Skin is especially good at gripping. It is soft enough to deform around small surface features, and its ridges increase the ways it can make contact. A slight amount of moisture can sometimes improve grip by increasing adhesion. Too much moisture does the opposite and forms a slippery layer. The difference between a secure grip and a dropped object can depend on a very thin film of water and a rather unfortunate moment of confidence. Our dependence on friction becomes clearer when it suddenly changes. Step onto dry stone and your brain barely considers the problem. Step onto ice, and your entire body becomes a cautious engineering project. Ice can be slippery for several reasons. Its surface may develop a very thin mobile layer, and pressure or heating from contact can also influence the interface between the ice and whatever is moving over it. The exact behavior depends on temperature, speed, pressure, and surface condition. Whatever combination is present, the grip between shoe and ground can fall sharply. Your walking style changes at once. Steps become shorter. Your feet remain flatter. You keep your center of mass more carefully above your support. You may extend your arms for balance and adopt the dignified posture of a penguin carrying invisible shopping bags. This instinctive adjustment shows how deeply friction is built into movement. Your nervous system is constantly estimating how much grip is available. It uses information from your feet, muscles, joints, eyes, and inner ear. When a surface feels uncertain, the body reduces the sideways force it asks the ground to provide. Friction also gives objects their sense of texture. When you run a finger across wood, paper, fabric, stone, or polished metal, the skin is not simply detecting bumps. It is responding to changes in resistance as the finger moves. Tiny variations in grip stretch the skin in different ways. Nerves detect these changes and the brain interprets them as smoothness, roughness, softness, stickiness, or dryness. A surface can feel rough even when the visible bumps are too small to see. It can also feel smooth while still producing considerable friction. This is another reason the usual picture of roughness alone is incomplete. Rough materials often create more resistance because their raised features collide, bend, or dig into one another. However, very smooth surfaces can sometimes create strong friction because they make closer contact. When two clean, flat materials meet closely, attractive forces between their atoms can become important. Small patches may adhere to one another, almost like tiny temporary bonds. As one surface slides, those connections must be stretched and broken. New connections then form elsewhere. The repeated creation and breaking of these contact points requires force, and that contributes to friction. This can happen even when neither object looks damaged. At a small enough scale, the surfaces are constantly changing. Microscopic pieces may transfer from one material to another. Tiny regions may warm, projections may flatten, soft sections may be dragged sideways. The visible objects remain almost the same, but their surfaces have been through a busy encounter. Consider rubbing your hands together. They become warm because the movement of your hands is being converted into irregular motion within the materials. Large-scale, organized motion becomes microscopic vibration and deformation. That microscopic activity is what we experience as heat. Friction does not create energy from nothing. The energy comes from your muscles. Your body uses stored chemical energy to move your hands. Friction changes some of that organized movement into thermal energy, leaving the skin slightly warmer. The same process appears in brakes. Brake pads press against a rotating disc or drum. Friction removes organised motion from the wheel and turns much of it into heat. During hard braking, the temperature can become extremely high. The vehicle slows because its motion has been redistributed into microscopic motion inside the brake materials, tyres, road and surrounding air. A match uses friction in a more dramatic way. Rubbing the match head against a prepared surface creates enough local heating to begin chemical reactions. The rough surface increases contact and deformation, while the force of the hand supplies the energy. Friction starts the process and combustion quickly takes over. Long before matches, people used friction to help start fires by rubbing or drilling pieces of wood. This method is difficult because wood also loses heat to the surrounding material and air. The rubbing must generate heat faster than the heat escapes. Anyone who has tried it may develop a new respect for both friction and modern lighters. Friction can be helpful, but it also causes wear. Shoe soles thin, tyres lose tread, pencil tips become blunt. Machine parts gradually change shape. Each sliding contact may remove only a tiny amount of material, but repeated many times, those losses become visible. Wear and friction are related, though they are not identical. A surface can produce strong friction without wearing quickly, and a material can wear even when the frictional resistance is not especially high. Wear depends on hardness, toughness, temperature, pressure, speed, surface contamination, and the way the materials interact. Engineers study these details because friction can be expensive. Machines lose useful energy through heating. Moving components require maintenance. Parts must be replaced. Surfaces can seize together if lubrication fails. At the same time, engineers cannot simply remove friction. A machine with no friction at all would create a different collection of problems. Screws might loosen. Belts could not transfer motion. Tyres could not grip roads. Tools would slide in the hand. Materials could not be sanded, polished, or cut in familiar ways. The goal is usually control rather than elimination. We want strong friction in shoes, tyres, climbing equipment, brakes, and gripping tools. We want low friction in bearings, engines, hinges, and sliding mechanisms. Sometimes the same machine needs high friction in one location, and very low friction only a few centimetres away. A bicycle is a good example. The tyres need grip against the road. The brake pads need friction against the wheel or disc. The rider needs friction between hands and handlebars and between shoes and pedals. Inside the wheel hubs, however, bearings are designed to reduce friction so the wheels can turn freely. The chain needs to grip the teeth of the gears. Yet the moving links also need lubrication to reduce resistance and wear. A bicycle may appear simple, but it is really a carefully arranged collection of places where friction is encouraged, limited, redirected, and occasionally blamed for a squeaking sound that no one can locate. Nature also makes extensive use of friction. Animal feet have claws, pads, scales, hairs, and textured skin that interact with surfaces in different ways. A cat can grip while climbing because its claws press into soft material. A gecko relies on enormous numbers of extremely fine structures on its feet. These allow very close contact with surfaces, making weak molecular attractions add together into a useful adhesive force. Insects use tiny hooks, pads, hairs, and secreted fluids. Snakes push sideways against irregularities in the ground. Birds grip branches with feet that wrap around the surface. Each solution works with the same basic challenge. An animal must push against its environment without sliding where it does not intend to slide. Plants also deal with friction. Seeds catch on fur, vines grip supports, roots press against soil particles. Bark offers traction to climbing animals and resistance to weather. Even the movement of water through a plant involves resistance along narrow passages, although that belongs to a wider family of interactions involving fluids. Friction is not limited to solid surfaces. Air resists moving objects. Water resists swimmers and boats. honey resists stirring far more strongly than water. These effects are often called drag or fluid resistance, rather than ordinary dry friction, but they share an important feature. They oppose relative movement and convert organised motion into less organised microscopic motion. The source is different in detail because a fluid can flow, change shape, and move around an object. Still, the underlying interactions ultimately involve particles pushing, attracting, colliding, and exchanging energy. This brings us closer to the central question: where does friction get its grip from? It does not come from a single mechanism hidden inside every surface. Friction is a result that can arise from several processes working together. Rough projections collide, soft materials deform, hard features plough through weaker ones, small contact regions adhere, molecules attract each other, loose particles roll or scrape between surfaces, thin films of water, oil, dust or grease alter the contact. The balance changes with the materials involved. Rubber on dry road behaves differently from steel on ice. Wood on wood differs from glass on glass. Clean surfaces differ from dusty ones. Slow movement can differ from fast movement. Warm surfaces may behave differently from cold surfaces. A gentle load does not always behave like a heavy load. That variety is why simple rules about friction work well in many ordinary situations but fail in others. In school experiments, the frictional force is often treated as depending mainly on how strongly two surfaces are pressed together and on the nature of the materials. This model is useful for block sliding across tables and many everyday calculations. Real surfaces, however, can be more complicated. Rubber changes shape. Polymers respond differently at different speeds. Metals may weld at microscopic contact points. Lubricants can form films that separate surfaces almost completely, or films so thin that occasional solid contact still occurs. At very small scales, even a single layer of atoms can change the behaviour. The visible size of the contact area can also be deceptive. Place a rectangular block flat on a table, then turn it onto a narrower side. You might expect the larger face to create much more friction, because more surface is touching. In many simple dry contacts, the friction may remain roughly similar. The reason lies in the true contact area. The surfaces meet only at microscopic high points. When the block rests on a smaller visible face, the pressure becomes greater, flattening those high points more strongly. The true microscopic area of contact can end up being comparable. This is not a perfect rule for every material. Soft rubber, sticky surfaces and materials that deform significantly can behave differently. Yet it reveals how little the visible surface tells us. What matters is the hidden contact taking place beneath the scale of ordinary sight. Even the word contact needs care. Atoms do not touch like solid miniature balls with sharp boundaries. Their electron distributions interact through electromagnetic forces. When surfaces are pressed together, the atoms approach until attractive and repulsive effects create a balance. Push harder, and the electron structures resist further overlap very strongly. The solid feeling of a table beneath your hand comes largely from these electromagnetic interactions. The table is not allowing the atoms of your hand to pass through its atoms. At the interface, those same interactions help determine adhesion, deformation, and resistance to sliding. Friction, therefore, begins in a place we cannot directly see. It emerges from many atomic interactions spread across countless tiny regions. No single atom decides to stop a shoe, hold a cup, or warm a brake pad. The familiar force appears when an enormous number of small events combine. That is part of what makes friction easy to use and difficult to explain. We experience it as one steady resistance, but underneath, it is a rapid sequence of contacts forming, changing, and breaking. Think again about your hand resting on a blanket or mattress. Nothing appears to be happening, yet gravity is pulling your hand downward. The material beneath it is deforming. Fibers are pressing against skin. Microscopic contact regions are supporting the load. If you try to move your hand sideways, those regions will initially resist. Push gently, and the hand may remain still. Push a little harder, and it may suddenly begin to slide. The resistance before motion begins is not always the same as the resistance during motion. That small difference explains why furniture can be hard to start moving and easier to keep moving, why a stuck lid suddenly gives way, and why tyres behave differently when rolling cleanly compared with skidding. For now, it is enough to notice that friction does not wait until something is already sliding. It can act while surfaces remain still, adjusting itself to match an applied force up to a limit. A book resting on a slightly tilted table may stay in place because friction balances the pull down the slope. Increase the tilt and eventually the grip reaches its limit. The book begins to move, usually at the exact moment someone has placed a cup beside it. That change from holding to slipping will become important as we continue. Before reaching it though, we need to look more closely at the hidden landscape where the grip begins. A tabletop that appears smooth is a field of microscopic peaks. A fingertip is a soft, ridged material filled with moisture, oils, and living tissue. A piece of metal carries scratches, oxide layers, dust, and tiny regions with different structures. When these surfaces meet, the contact is far more complicated than two neat flat planes pressing together. Some of the smallest forces involved are familiar electromagnetic attractions. Others come from material being bent, compressed, torn, or dragged. Together they determine whether an object remains fixed, begins to slide, moves smoothly, chatters, squeaks, heats, wears, or suddenly sticks. The grip of friction starts there, in the scattered places where matter comes close enough to notice other matter. To understand what happens in those scattered places, we need to move far below the level of scratches, fingerprints, and grains of dust. We need to imagine the surfaces becoming larger and larger until a polished table begins to resemble a landscape, then keep going until even that landscape disappears and individual atoms become part of the picture. At this scale, the word touch becomes more complicated than it sounds. When you place your hand on a table, it feels as though the skin and the wood are pressed directly together. The table supports your weight. Your hand cannot pass through it. Everything about the experience suggests solid contact between two clearly defined objects. Atoms, however, do not have hard outer shells like tiny billiard balls. They are mostly regions of electric charge, with electrons spread around much smaller central nuclei. The edges of those regions are not sharp. There is no exact surface where one atom ends in the ordinary sense and another begins. As the atoms in your hand approach the atoms in the table, their electrons begin to interact. Electrical repulsion grows rapidly when the electron regions are pushed too close together. Quantum rules also prevent the electrons from all settling into the same available states. Together, these effects make matter resist compression and prevent one solid object from passing casually through another. The firmness of the table is therefore not caused by little solid spheres colliding. It comes mainly from invisible interactions between electric charges and the rules governing electrons. That may feel slightly disappointing if you had imagined atoms as neat marbles stacked inside everything. The reality is less tidy, but it is much more useful. It explains why objects can feel solid, even though atoms contain so much empty space. It also brings us closer to the origin of friction, because the same interactions that stop surfaces from passing through each other also influence what happens when they try to slide. Picture two pieces of clean metal pressed together. To the eye, each piece may look flat. Under strong magnification, both surfaces would show ridges and peaks. Only the highest points meet at first. The rest of the visible area remains separated by tiny gaps filled with air, moisture, dust, or nothing substantial at all. The load on the metal is carried by those small contact points. Because the true area is so limited, the pressure at each point can be enormous. A force spread across the apparent face of an object becomes concentrated into microscopic regions. Those regions may deform under the pressure. A sharp peak can flatten, a softer patch can spread. Two surfaces that seem to touch only lightly can develop small islands of close contact. Within those islands, Atoms from opposite surfaces approach closely enough for attractive forces to matter. The outer electrons respond to nearby atoms. Temporary attractions form. In some cases, particularly with very clean metals, the atoms can create junctions resembling weak microscopic welds. This does not mean that placing two spoons together will turn them into one larger and considerably less useful spoon. Ordinary metal surfaces are covered with oxide layers, oils, water, and contamination from the environment. These layers interfere with direct atomic contact. Still, at scattered points, enough attraction can develop to make the surfaces cling. When one piece begins to move, those tiny junctions must stretch, deform, and break. New junctions form ahead, while old ones fail behind. The repeated breaking of these connections contributes to the resistance we call friction. The process is not calm at the microscopic level. A block may appear to slide steadily across a table, but the contact beneath it can be full of sudden events. Small regions stick for a moment. Stress builds, a junction breaks. The surfaces jump forward by a tiny distance. Another region catches. The cycle repeats too quickly and at too small a scale for the eye to separate. Under certain conditions, these tiny starts and stops become large enough to notice. A door hinge squeaks. A violin string vibrates beneath a bow. A wet finger dragged around the rim of a glass can make the glass sing. Car brakes may shudder. Furniture moved across a floor can produce a series of unpleasant sounds that suggest the furniture has strong opinions about being relocated. These effects often involve a pattern called sticking and slipping. The surfaces hold together while force builds, then move suddenly when the grip fails. After slipping, they catch again. Repetition produces vibration, and vibration produces sound. A violin depends on this behavior. The bow is coated with rosin, which helps it grip the string. As the bow moves, the string sticks to it and is pulled sideways. Eventually, the restoring force in the stretched string becomes strong enough to make the string slip free. It snaps back, catches again, and repeats the motion. The instrument turns microscopic adhesion and repeated slipping into music. The same general process can create noises that are less welcome. A squeaking shoe on a polished floor, a creaking bed frame, or a windscreen wiper dragging across nearly dry glass all involve changing contact between materials. The sound is evidence that friction is not always a smooth force. It can rise, fall, and reorganize as surfaces move. Adhesion between atoms is only one source of resistance. Deformation matters too. Suppose a hard, rough surface slides across a softer material. The raised points on the hard surface can press into the softer one. As motion continues, those points push material aside, much like a plough moving through soil. Energy is required to deform the softer surface. Some of the material springs back after the object passes. Some remains permanently changed. Some may break away as wear particles. Rubber often behaves in this way. A rubber tyre pressing against a road bends around the road texture. As the tyre rolls, different parts of the rubber are repeatedly compressed, stretched, and released. Rubber does not return all the stored energy perfectly. Some is lost as heat. This internal energy loss contributes to rolling resistance. It is one reason a bicycle slows even when the wheel bearings are good and the road appears level. The tyres continually deform where they meet the ground. Each section flattens, carries the load, then regains its shape after leaving the contact region. A very soft tyre deforms more and usually wastes more energy. A properly inflated tyre deforms less, although the best pressure depends on the surface, tyre design, comfort, grip, and several other concerns that cyclists can discuss for an impressive length of time. Soft materials also create a larger true contact area. Press a fingertip onto glass and the skin spreads. Fine ridges flatten against the surface. More atoms are brought close enough to interact. This can increase adhesion and improve grip. That is why the texture of human skin is not the whole explanation for our ability to hold objects. Skin is flexible, slightly moist, and able to conform to small irregularities. It creates close contact across many tiny regions. The amount of moisture matters. Completely dry skin may grip some materials poorly because the contact is limited. A small amount of moisture can soften the outer skin and increase adhesion. Too much water can separate the surfaces and act as a lubricant. Anyone who has tried to open a smooth plastic bag with dry fingers may have discovered that friction sometimes requires a little assistance. The traditional solution is to touch the fingertips together, adjust the grip, and pretend that the previous attempts did not happen. Water between surfaces can behave in different ways. A thin layer may increase attraction through surface tension or capillary effects. A thicker layer can reduce direct contact and allow the surfaces to move more easily. Mud is another reminder that friction depends on the whole contact, not simply the two main materials. A boot on dry soil may grip well because the tread presses into firm particles. On wet clay, the water and fine sediment can form a slippery layer. The boot no longer interacts with solid ground in the same way. It slides across a deforming mixture that may remain attached to the sole. Oil is used deliberately to create separation. In a well-lubricated machine, the moving surfaces may be kept apart by a thin film of liquid. Instead of metal rubbing directly against metal, layers within the lubricant slide past each other. The friction does not disappear completely. The liquid resists flowing, and this creates drag. However, the resistance and wear can be far lower than direct solid contact. Lubrication also prevents microscopic junctions from forming between the main surfaces. Additives in oils can attach to metal and create protective layers. Some react under pressure or heat to produce films that reduce damage. Without lubrication, machine parts can become hot, rough, and increasingly difficult to move. The surfaces may scrape away material. Contact points can weld and tear apart. In severe cases, the parts seize together. An engine contains many places where thin films must survive under heavy loads and high temperatures. Oil is pumped between moving components, carrying heat away and reducing direct contact. The system depends on maintaining the right viscosity, pressure, cleanliness, and temperature. Oil that's too thick creates unnecessary resistance. Oil that's too thin may fail to keep surfaces separated. Contamination can introduce hard particles that scratch components. The humble lubricant has a demanding job, even if its public reputation rarely extends beyond stains and inconvenient warning lights. Dust also changes friction. A few particles between surfaces may increase resistance by creating rough obstacles. Other particles can act like tiny rollers and reduce it. Powdered graphite is used as a dry lubricant because its internal layers can slide over one another relatively easily. Sand on ice can increase grip by creating hard points that press into the surface. Sand between moving machine parts can cause rapid wear. The effect depends on the particles, the surfaces, the load, and whether the particles roll, slide, crush, or become embedded. This variety tells us that friction is not a permanent property belonging to one object. A material does not carry a fixed amount of friction inside it. Friction describes an interaction between surfaces under particular conditions. Rubber may grip dry pavement strongly, yet slide more easily on water or loose gravel. Steel may move smoothly over polished steel when lubricated, but resist strongly if the surfaces are clean and pressed together. Wood behaves differently depending on grain direction, moisture, finish, and wear. Temperature can change the interaction. Warm rubber becomes softer and can conform more closely to road texture. Excessive heat may weaken it or change the way its molecules respond. Ice becomes more slippery across some temperature ranges because the behavior of its surface layer changes. Speed matters as well. Some materials have more friction at low speed and less at high speed. Others behave in the opposite way. A lubricant can form a stronger separating film when surfaces move quickly, while slow movement may allow more direct contact. Pressure changes the true contact area and can alter the materials themselves. A soft surface may spread, a hard coating may crack, A thin film may be squeezed out. Under extreme pressure, atoms may be forced close enough for stronger bonding or structural change. Even the length of time that surfaces remain pressed together can matter. If two materials rest in contact, their microscopic junctions may slowly grow. Soft regions deform, molecules rearrange, moisture moves. The surfaces can become harder to separate after waiting. This helps explain why an object that has remained still for a long period may require a stronger initial push than one that was placed down only moments ago. It also contributes to the behavior of adhesives, seals, tires, and biological tissue. At the atomic level, attraction itself comes in several forms. Atoms and molecules can develop uneven distributions of electric charge. Even when a molecule has no permanent positive or negative side, its electrons are always moving. For an instant, more charge may appear on one side than the other. That temporary imbalance can influence a neighbouring molecule, creating a weak attraction. Individually, these forces are small. Across a large number of closely spaced atoms, they can become important. Some molecules have permanent regions of partial charge and interact more strongly. Hydrogen bonding can add further attraction in materials containing suitable chemical groups. In other cases, electrons may be shared more directly across an interface. We do not need to list every type of atomic attraction to understand the main point. When surfaces come very close, the atoms on one side are not indifferent to the atoms on the other. Their electric structures respond. They attract at some distances and repel strongly at shorter ones. The balance of these forces helps determine whether the surfaces adhere, separate easily, or resist sliding. At first, it may seem strange that weak atomic attractions can affect something as large as a shoe, tyre, or brake pad. The answer lies in numbers. A single interaction is tiny, but a contact surface contains an enormous number of atoms. Not all of them participate equally. Most remain too far apart because of roughness and contamination. Yet the atoms within the true contact regions are numerous enough for their combined effect to become visible at the human scale. A similar principle allows a gecko to climb smooth walls. The fine structures on its feet divide into smaller and smaller branches. This creates very close contact over a large effective area. Weak attractions between the foot and the wall add together. The gecko does not use glue in the ordinary sense. It controls the angle and loading of the tiny structures, engaging and releasing them as it moves. A force that is weak for one molecular contact becomes useful when repeated across millions of contacts. Human-made materials can borrow this idea. Researchers have developed dry adhesives with fine structures inspired by gecko feet. Such surfaces may grip without leaving sticky residue and release when pulled in a particular direction. The challenge is not simply creating attraction. The material must make close contact, carry a useful load, avoid collecting dirt and release when required. Nature has had a considerable period of testing, while engineers are expected to produce similar results before the next funding review. Atomic attraction also explains why extremely clean flat surfaces can stick unexpectedly. In a vacuum, metal surfaces may be free from the oxide and contamination layers that normally keep them apart. When pressed together, atoms across the interface can bond so strongly that the pieces cold weld. This can cause problems in spacecraft and vacuum equipment. Components designed to slide or separate on Earth may behave differently when the protective surface layers are absent. Engineers choose materials, coatings, and lubricants carefully to prevent unwanted adhesion. The atmosphere around us is therefore part of ordinary friction. Oxygen reacts with metals to form oxide layers. Water molecules settle on surfaces. Air carries organic compounds and dust. Our hands leave oils and skin cells behind. A surface that appears clean is usually chemically busy. These thin layers can reduce direct bonding, increase it, or introduce entirely new forms of resistance. Friction is therefore shaped by objects that may not seem to be part of the contact. The surrounding air, humidity, temperature and history of the surfaces all matter. A metal part freshly cut in a workshop may behave differently after sitting in the open. Glass cleaned with one substance may grip differently from glass cleaned with another. This sensitivity can make precise friction experiments difficult. Two tests using the same name materials may give different results if their surfaces were prepared differently. Tiny scratches, oils, dust, and wear from earlier tests can change the outcome. Scientists who study friction often work with carefully controlled surfaces. They may clean samples in vacuum, use microscopes to measure roughness, and control temperature and humidity. Instruments can detect forces between a very small tip and a surface, allowing researchers to investigate friction at the scale of individual contact regions. At such small scales, familiar rules can change. The weight of an object may become less important than adhesion. Surface forces dominate because very small objects have a large surface area compared with their volume. A tiny particle may cling stubbornly to a surface even when gravity is trying to pull it away. This is why fine dust sticks to screens, lenses, and equipment. It is also why microscopic machines face unusual problems. Their components can become trapped by surface attraction. For a person, gravity is obvious. For a microscopic mechanism, adhesion can be the greater concern. A gear smaller than a grain of sand may not behave like a reduced version of a bicycle gear. The forces that matter most have changed. This difference appears in biology as well. Small insects can stand on ceilings because their low weight is easier to support with adhesive contact. Water behaves differently around tiny structures because surface tension becomes especially important. Pollen grains cling. Cells attach to tissues. Bacteria adhere to surfaces and form communities. The physical world does not have one preferred scale. The rules are consistent, but the relative importance of different effects changes with size. Friction sits at the meeting point between those scales. Its origin is atomic, yet its results shape walking, transport, manufacturing, geology, weather, and life. Deep underground, enormous masses of rock press against faults. The surfaces may lock through rough contact, mineral bonding, and deformation. Stress builds slowly as tectonic plates move. When the grip fails, the rocks slip and release energy as an earthquake. The event is far larger than anything in a laboratory, but the fault still depends on contact between irregular materials. Fluids can enter the rock and change the pressure. Heat can alter minerals. Fragments can grind into powder. Smooth movement can shift into sudden slipping. At the other end of the scale, a microscope tip dragged across a single layer of atoms can display its own pattern of sticking and release. The distances and forces are tiny, yet the basic question remains familiar. How do two pieces of matter resist moving past each other? There is no single answer because the contact keeps changing. Atoms attract and repel. Surface peaks deform. Junctions form and break. Molecules rearrange. Heat spreads. Material transfers. Films flow. Particles roll and scrape. Each process contributes according to the situation. This is why friction can be dependable enough to let you walk across a room and unpredictable enough to make a jar lid defeat 3 adults before opening easily for someone who claims not to have tried very hard. The jar lid may be held by several effects at once. The threads press together. A seal creates additional resistance. Temperature changes the size of the materials. Dried food may act as an adhesive. Your fingers need enough friction against the lid to apply a turning force. Running warm water over the lid can expand the metal and soften residue. A cloth or rubber grip increases contact with the hand. Tapping can break stuck regions. What feels like one stubborn problem is really a group of interactions cooperating against dinner. The atomic picture does not make friction less ordinary. It reveals how much is happening inside ordinary contact. Rest your hand on a surface again and notice the stillness. Beneath that stillness, the skin is pressed into microscopic features. Molecules are close enough to attract. Electrons resist being forced together. Soft tissue is deformed. Moisture is redistributed. Move the hand slightly and the contact reorganizes. Some regions release. Others form. Energy becomes heat. Nerves detect changing stress and report texture to the brain. The entire experience of touch depends on these interactions. Without resistance between skin and object, surfaces would be much harder to distinguish. Tools would be difficult to control. Writing, climbing, eating, building, and nearly every careful movement of the hands would change. Friction gets its grip from the invisible behavior of matter at the interface. It is not a hidden substance between objects and not a simple consequence of visible roughness. It is the large result of countless small interactions. Those interactions begin with atoms coming close, but the shape of the surfaces decides where that closeness occurs. A surface that looks smooth may touch only at a collection of tiny peaks, while a soft material may spread and create broad contact. That hidden geometry now needs our attention, because roughness matters greatly, just not in the simple way it's usually imagined. A rough surface seems like the obvious place for friction to begin. Run your hand across unfinished wood, concrete, sandpaper, or the edge of an old brick, and the resistance is easy to feel. The raised pieces catch against your skin. Small ridges press into one another. Movement becomes harder than it would be across polished glass or smooth metal. From that experience, it is tempting to imagine friction as nothing more than microscopic bumps colliding. One surface has peaks and valleys. The other surface has its own peaks and valleys. Push them together, and the peaks lock like the teeth of two combs. To make the surfaces move, those teeth must climb over one another. That picture is useful, and sometimes it describes an important part of what is happening. It is not completely wrong, it is simply incomplete. Some rough surfaces produce a great deal of friction, others do not. Some smooth surfaces slide easily, others grip so strongly that separating them becomes difficult. Rubber can cling to polished glass even though neither looks particularly rough. Two smooth pieces of clean metal can resist sliding because tiny regions join together. A layer of loose powder can make a rough floor more slippery rather than less. The amount of visible roughness cannot tell us everything about the grip between materials. Part of the confusion comes from the way we use the word smooth. A surface may look smooth because the irregularities are too small for our eyes to see. It may feel smooth because its larger bumps do not press sharply into the skin. Under a microscope, however, that same surface can look like uneven ground. Polished steel contains scratches, pits, ridges, and flattened patches. Glass contains small variations in height and chemical composition. Plastic may carry moulding marks, dust, oils, and damaged regions. Paper is a tangled field of fibres. Skin is made of ridges, folds, pores, loose cells, moisture, and natural oils. There is no perfectly flat everyday surface. When two objects are placed together, the highest points meet first. These high points are sometimes called asperities, although we can simply think of them as microscopic peaks. The visible faces of the objects may appear to touch across a broad area, but most of that area remains separated by tiny gaps. A wooden block sitting on a table may have a base covering many square centimetres. The true contact is concentrated at scattered points far smaller than the apparent base. Those points carry the entire weight of the block. This means the pressure at each contact can be much higher than we might expect. Pressure that seems modest when averaged across the visible area becomes concentrated onto a collection of microscopic islands. The peaks bend, flatten, or press into one another. Softer materials deform more easily. Hard materials may resist deformation but can still change slightly under enough pressure. Atoms shift. Crystal structures bend. Thin coatings crack or compress. The true contact area grows until enough of the surface is supporting the load. This hidden area is one of the most important parts of friction. Imagine pressing a dry sponge against a table. Touch it lightly, and only the highest parts make contact. Push harder and the sponge flattens, spreading across a larger area. More of its structure meets the table. Metal does something similar, although the change is too small to see, and the material is much stiffer. At microscopic peaks, the pressure can become high enough to deform the metal locally. The block does not look flatter afterward, but its smallest contact points have adjusted. As the load increases, more peaks are brought into contact and existing peaks spread. The real area of contact becomes larger. This gives more places for adhesion, deformation, and resistance to sliding. That helps explain why friction often increases when two surfaces are pressed together more strongly. A heavy box is usually harder to slide than a light one made from the same materials. The added weight increases the load at the interface. More microscopic contact develops, and the combined resistance becomes greater. The simple image of rigid teeth locking together misses this deformation. Real peaks are not always hard, fixed obstacles. They bend, squash, scrape, fracture, and change shape. The image also creates another problem. If friction came mainly from large bumps climbing over one another, lifting would occur whenever an object slid. The object would repeatedly rise and fall as its surface crossed the uneven ground. Some of that can happen, particularly on very rough surfaces. A heavy crate dragged across broken stone may bounce and tilt. The edges of the material may catch against large features. Energy is used to lift, deform, and damage the surfaces. At smaller scales, though, the motion is not simply a neat climb over fixed hills. The contact points can shear apart. A peak may be sliced, bent sideways, or pressed into the other material. Adhesive junctions may break before one surface has climbed over the other. Roughness contributes, but its effect depends on what the rough features do. Sandpaper is designed to create strong local pressure. Hard abrasive grains stand above the backing material. When rubbed against wood, paint, or metal, those grains press into the surface and remove small pieces. The resistance felt during sanding comes partly from the grains pushing through the material. This is sometimes described as ploughing. The grains make tiny grooves, displace material, and break fragments away. A finer sandpaper has smaller abrasive particles. It usually removes less material with each pass and leaves shallower scratches. Coarse sandpaper cuts more aggressively because its larger grains dig more deeply. The roughness has a clear role here, but the friction is connected to damage and deformation. The grains are not merely bumping against the surface, they are cutting it. A rough road interacts with a tire in another way. Rubber is soft and flexible. It bends around stones and texture in the road. As the tire rolls, the rubber enters each uneven region, changes shape, and then tries to recover. Rubber does not return all the energy used to deform it. Some energy becomes heat inside the material. This internal loss contributes to the resistance between tire and road. The road texture also creates sideways support. The rubber presses around small features, giving the contact resistance against sliding. Yet a road can become less grippy when covered by loose gravel. The tire may then roll or slide over moving stones rather than pressing directly against a stable surface. The gravel is rough, but it does not provide the same secure contact. Individual pieces can move, rotate, and scatter. The tire grips the gravel while the gravel fails to grip the ground beneath it. A similar effect occurs when dust or sand collects on a hard floor. The particles may act as tiny rollers. Instead of two solid surfaces rubbing directly, the loose grains move between them. A shoe can slip even though the particles themselves feel rough. This is why adding rough material does not automatically increase friction. The roughness must be attached firmly enough to carry force. Ice offers another example. Scratching an icy surface may increase grip by creating edges that a boot can press against. Adding grit can provide firm contact points. Loose snow, however, may compress and slide between the boot and the ice. The result depends on temperature, pressure, particle size, and whether the loose material remains stable. Roughness works through the entire structure of the contact, not through appearance alone. Smoothness can also increase friction. Take two clean pieces of soft metal with carefully flattened surfaces. Because the surfaces are smooth, more microscopic regions may approach closely. adhesive attraction can develop across a larger true contact area. Small junctions can form between the metals. Sliding requires those junctions to break. The resistance may be greater than it would be for surfaces with rough features that keep much of the material apart. Extremely smooth surfaces can even become difficult to separate. Two clean glass plates with a thin film of water between them may cling together. The water spreads into a narrow layer, and surface tension helps hold the plates close. Pulling them directly apart can require considerable force, while sliding them sideways may be easier. The glass is not gripping because large bumps are locked. The behaviour comes from close contact, liquid forces, and the geometry of the thin gap. A suction cup also attaches to smooth surfaces more effectively than rough ones. Pressing it against glass removes much of the air beneath it. The flexible rim forms a seal. Air pressure outside helps hold the cup in place. On rough stone, gaps under the rim allow air to leak in. The cup may fail even though the stone offers more visible texture. This is not ordinary dry friction by itself, but it is a useful warning. Roughness can reduce contact and prevent other forces from working. Adhesive tape provides another clear example. Tape usually sticks better to a clean, smooth surface than to a dusty, uneven one. The adhesive is soft and able to flow into small irregularities. To grip well, it needs close contact. On a rough wall, the tape may touch only the highest points. On a dusty surface, it sticks to loose particles rather than to the wall. Those particles then pull away easily. Pressing the tape firmly increases its contact. The adhesive spreads, fills small spaces, and approaches the surface closely enough for molecular attractions to act. The grip comes from an enormous number of weak interactions across the interface. The same principle appears in friction between many soft materials. Close contact can matter more than visible texture. Rubber gloves often grip smooth objects well. A smooth rubber sole may provide strong traction on a clean, dry floor. The rubber deforms and creates a large real contact area. Adhesive forces and internal deformation both contribute. Add water, oil, or powder, and the behaviour changes. The extra layer separates the rubber from the floor or allows sliding within the layer. The visible roughness of the two main surfaces may remain the same, but the grip falls. Tyre tread is sometimes misunderstood for this reason. On a dry, clean road, a larger area of rubber in contact with the surface can provide strong grip. Racing tyres used in dry conditions may have very little tread, because grooves reduce the amount of rubber touching the road. In rain, the situation changes. Water must escape from beneath the tyre. Tread grooves give it pathways to move away. Without those pathways, water can build into a layer that separates the tyre from the road. The tread is not useful simply because it makes the tyre rougher. Its shape manages water, preserves contact, deforms against the road, and provides edges that interact with the surface. On mud, snow, or loose ground, deeper tread can press into the material and push against it. The tyre may gain traction by moving soil or compacting snow. Once again, the reason depends on the contact conditions. A surface feature that is helpful in one environment may be useless in another. Footwear designers face the same problem. A sole for polished indoor floors needs different properties from a sole for wet rock, snow, loose soil, or artificial sport surfaces. Material softness, tread depth, groove direction, edge shape, and drainage all matter. A hiking boot with deep lugs can grip soft ground because the lugs sink in and push against the soil. On smooth, wet stone, those same lugs may create less contact than a softer, flatter sole. A rock climbing shoe uses soft rubber and a relatively smooth shape to create close contact with rock. The climber presses the foot against small holds, and the rubber deforms around fine texture. A football boot uses studs because the ground is soft enough for them to penetrate. The studs create support by pushing against the soil. Wearing those boots on a polished floor would not produce the same benefit, and would create a memorable walk for all the wrong reasons. Grip is always a partnership between the surface and the object. The direction of roughness matters too. Wood has grain. Brushed metal contains aligned scratches. Fabric has fibers arranged in particular patterns. Animal skin, scales, and hairs may be angled so that movement is easier in one direction than another. Run a hand along some fabrics and the resistance changes when you reverse direction. Fine hairs lie flat one way and stand up the other. The surface has directional friction. Snakes use the direction and shape of their scales to push against the ground. The scales resist motion differently depending on the direction of force. This helps the animal move forward while limiting unwanted sideways slipping. Some plant seeds have hooks or barbs that catch more strongly in one direction. Climbing equipment, conveyor belts, and specialized gripping surfaces can be designed to do the same. A simple measurement of how rough a surface is would not fully describe this behavior. We would also need to know the shape, orientation, spacing, flexibility, and strength of the features. Scale makes the problem even more interesting. A surface may be rough at one scale and smooth at another. A sheet of paper looks flat from across a room. Up close, its fibers become visible. At a smaller scale, the fibers have their own texture. At an even smaller scale, molecules and chemical groups determine the local interactions. A road is rough compared with a tire. A polished metal plate is rough compared with a microscopic probe. A mountain range is rough compared with a car but may look nearly smooth from orbit. There is no single size at which roughness should be judged. The important scale depends on the object making contact. A large soft tire responds to road features of many sizes. Very small irregularities influence adhesion and rubber deformation. Larger stones influence the overall shape of the contact. Deep holes affect the wheel and suspension. A tiny insect foot experiences the same surface differently. Features that seem smooth to us may be enormous obstacles to the insect. Fine hairs on its foot may fit into gaps that a large object bridges over. When scientists describe a surface, they often measure more than average roughness. They examine peak height, spacing, slope, shape, and the way features are distributed across different scales. Two surfaces can have the same average roughness and produce different friction. One may have broad rounded hills, another may have narrow sharp peaks. The sharp peaks create higher local pressure and may scratch or cut the opposing material. A surface with widely spaced features may touch differently from one with many closely packed features. A material with flexible peaks may bend rather than dig in. A brittle peak may break away and become a loose particle. The history of the surface also matters. Sliding changes roughness. At first, two fresh surfaces may meet at sharp peaks. During use, those peaks flatten, break, or become polished. Where particles may fill the valleys, material from one surface may transfer to the other. Friction can rise or fall as this happens. A rough machine part may become smoother during an early period of operation. Engineers sometimes expect a controlled wearing and process before performance becomes stable. In other cases, damage makes the surface rougher. Scratches grow, protective coatings fail. Loose fragments become trapped in the contact. Resistance and wear increase together. Brake pads and discs develop working surfaces through repeated contact. Tires change as tread wears and rubber ages. Shoe soles polish in the areas carrying the most load. A frequently used wooden stair becomes rounded and smooth. The surfaces we use are not permanent. Each contact leaves a small record of previous movement. Cleaning can change that record. Removing oil may increase friction by allowing closer solid contact. Removing sticky contamination may reduce friction. Polishing may lower roughness while increasing the true contact area. Wax can fill valleys and create a low resistance layer. A polished wooden floor may be slippery because the coating is smooth, hard, and offers limited deformation to a shoe. A polished rubber surface may still grip well because the rubber remains soft and adhesive. The word polished does not predict the outcome without knowing the materials. Engineers sometimes add texture deliberately. Small grooves can hold lubricant. Pits can trap wear particles. Surface patterns can direct water. A roughened metal surface may help paint or glue attach by increasing area and creating places for mechanical anchoring. Too much roughness can be harmful. Deep peaks may reduce true contact, concentrate stress, tear the opposing material, or squeeze lubricant away. The most effective surface is rarely the roughest possible one. There is often an appropriate range of texture for a particular task. A brake pad needs enough interaction with the disc to produce controlled resistance. It also needs to survive heat and wear. A seal needs close contact to prevent leakage, but may need lubrication to avoid damage. A touchscreen must remain smooth to the finger, while still allowing controlled movement. A prosthetic joint aims for extremely low friction and low wear over years of use. Each design involves more than making one surface rough and the other smooth. Human touch is sensitive to these details. When you move a finger over a surface, the skin stretches and vibrates. Fine texture produces rapid vibrations. Larger features create slower changes in pressure. The ridges of the fingerprint interact with the surface and may amplify certain vibrations. Nerves in the skin respond to different patterns. The brain combines that information into a sense of texture. A surface can feel rough because of vibration even when the finger is not being blocked by large features. It can feel sticky because the resistance changes as the skin alternately grips and releases. This is why texture and friction are related but not identical. A surface that feels rough may not require the greatest force to slide across it. A smooth, sticky surface may create stronger resistance than a dry, rough one. Try moving a finger across clean glass. Under some conditions, the movement is smooth and easy. Under others, the finger catches and jumps. Moisture, pressure, skin condition, and speed all change the result. The glass has not suddenly grown bumps. The contact has changed. Speed can alter how roughness affects a material. Move rubber slowly across a textured surface, and it has time to deform around the features. Move it quickly, and the rubber responds differently. Its stiffness effectively changes with the rate of deformation. At certain speeds, the texture causes strong internal energy loss. At others, the rubber may not settle deeply into every valley. Temperature changes this response as well. This is one reason tyre grip cannot be described by a single permanent number. Speed, temperature, road condition, tyre pressure, and rubber composition all influence the contact. Even very hard surfaces change with speed. Rapid sliding generates heat. Heat can soften materials, change coatings, evaporate moisture, or alter lubricant. The contact may begin in one condition and move into another. A block starting from rest may resist strongly. Once it is moving, the junctions have less time to grow. Friction may decrease. In other situations, faster movement increases deformation, or fluid resistance and friction rises. Roughness helps determine where the surfaces meet, but it does not decide by itself what happens there. The full grip comes from a combination of true contact area, adhesion, deformation, ploughing, material strength, loose particles, thin films, speed, temperature and pressure. Roughness influences nearly all of these, yet its role changes from one pair of materials to another. This gives us a more useful picture than the familiar rows of interlocking teeth. Imagine a collection of contact islands. Some are strong and some are weak. Some are dry. Some contain water, oil, dust, or fragments. At one island, the materials adhere. At another, a hard peak cuts into a soft surface. Elsewhere, rubber bends around a ridge. A nearby particle rolls between the objects. When the object is still, these islands share the applied force. Some junctions stretch, soft areas deform, new contact develops as pressure shifts. The surfaces can resist without moving because the microscopic structures are not perfectly rigid. They adjust to the force, push a little and they push back, push more and the resistance increases. That resistance does not grow forever. Each contact has a limit. Junctions can break, peaks can bend too far, a soft region can tear, particles can begin to roll. Once enough of the contact network fails, the object starts to move. The difference between holding and sliding is not simply a rough edge climbing over another rough edge. It is a change across many microscopic contacts. A stable network becomes an unstable one. The surfaces lose their temporary grip and reorganize while moving. That is why an object can remain completely still under a small sideways force, resist a larger one, and then suddenly break free. The roughness helps decide where the grip forms. The materials decide how strongly those places hold. Pressure decides how many contact regions develop. Time allows some of them to grow. The applied force stretches the entire network until it reaches the point where holding can no longer continue. The grip before that first movement has its own behaviour, and it is often stronger and more adaptable than the friction that acts after sliding begins. That grip before the first movement has a special name. It is called static friction, and it is the reason objects can remain still even when something is trying to make them move. The word static means not moving. Static friction acts between surfaces that are touching without sliding across one another. It may hold a book on a tilted table, keep a parked car from rolling down a hill, stop a ladder from slipping, or allow your foot to push against the floor while you walk. It is easy to think of friction as a fixed force that is always present in the same amount. Static friction does not behave that way. It adjusts. Place a heavy box on a level floor and leave it alone. There is no sideways force trying to move it, so there is no sideways friction acting on it. The floor supports the box vertically, but static friction has no reason to act along the surface. Push the box very gently. If it stays still, static friction pushes back with an equal amount of force. Push a little harder, and static friction becomes a little stronger. The box still does not move. This continues until the contact reaches its limit. Static friction is therefore responsive. It does not begin at its greatest possible strength. It supplies only as much resistance as is needed to prevent sliding, up to the largest amount the surfaces can provide. This behaviour can feel almost deliberate. You push with a small force and the floor matches it. You push harder and the resistance increases. Nothing moves until the grip can no longer keep up. Of course, the floor is not measuring your effort or making decisions. The changing resistance comes from deformation at the contact points. When you begin to push the box, the microscopic junctions between the box and the floor stretch slightly. Surface peaks bend. Soft areas change shape. Adhesive contact regions are pulled sideways. These small changes create a restoring force that opposes your push. A weak push causes only a small deformation. A stronger push creates greater deformation and places more stress on the contact network. The box may look perfectly still, but its surfaces are already responding. The changes are simply too small to see. Imagine pressing the side of a rubber eraser while it rests on a table. Before the eraser slides, its shape changes. The upper part moves slightly while the bottom remains attached to the table. The rubber twists and stretches. If you stop pushing, the eraser returns to its earlier shape. The stored deformation releases, and the object remains where it started. Push farther and the bottom eventually loses its grip. The eraser slips. A hard wooden box changes far less visibly, but the same general idea applies. The material and the surface contact deform on a microscopic scale. Static friction is the combined resistance produced by that deformation and adhesion. The maximum grip depends strongly on how firmly the surfaces are pressed together. A heavy box is usually harder to start moving than a light one because its weight presses the contact points together more strongly. More microscopic regions support the load. Existing contacts flatten and spread. Adhesive junctions become larger or more numerous. This is why pressing downward on an object can make it harder to slide. You're increasing the contact load. Try moving a sheet of paper across a table with one fingertip resting lightly on it. Then press down more firmly and try again. The paper becomes harder to move because the stronger pressure creates more friction between the paper and the table. The same effect helps a person grip an object. Squeezing a glass more firmly increases the pressure between the fingers and the glass. Static friction can then provide a stronger upward force before slipping begins. There is a practical limit to this method. Squeezing delicate objects too firmly introduces a second problem, which is that they may break before they slip. Friction may have succeeded, but the celebration will be brief. The nature of the materials also matters. Rubber on dry concrete can produce strong static friction because the rubber deforms around the surface texture and creates close contact. Smooth hard plastic on polished metal may provide much less grip. Water, dust, grease and loose particles can change the limit. A clean shoe sole may hold securely on a dry floor but slide on a thin layer of oil. The pressure may be the same, but the contact is no longer between the same surfaces. Static friction is not a property of one object. It belongs to the entire situation. Consider a book resting on a table that is slowly being tilted. At first, the book remains still. Gravity pulls downward, but part of that pull acts along the sloping surface. Static friction acts in the opposite direction and prevents the book from sliding. As the table becomes steeper, the pull along the surface increases. Static friction increases to match it. The book remains still until the required friction becomes greater than the contact can supply. At that point, the book begins to slide. The movement may seem sudden because the system passes from one condition to another. A moment earlier, the contact network could hold. A moment later, enough junctions have failed that motion begins. This is why slowly increasing a force can produce a sudden release. A stuck drawer does not always move gradually as you pull harder. It resists again, and then opens with enough enthusiasm to make you step backward. A jar lid behaves similarly. Your hand applies a turning force. Static friction between your fingers and the lid must be strong enough to prevent your skin from slipping. Static friction within the threads and seal must also be overcome. At first, the entire system remains still. Pressure builds in your skin and in the lid. Small regions deform. Stuck contact points are stressed. Once the resisting contacts fail, the lid may rotate suddenly. Your hand continues moving for a moment because your muscles were prepared to overcome a larger resistance. This difference between holding and slipping affects many ordinary actions. When you walk, the part of your shoe touching the ground is normally not sliding backward. Your foot pushes backward against the floor, but static friction keeps the contact fixed. The floor then pushes your body forward. If the required grip stays below the maximum available amount, the step is secure. On ice, the maximum static friction is much lower. A strong backward push can exceed the available grip. The foot then slides, and your body does not move forward in the intended way. People naturally take smaller steps on slippery surfaces because smaller steps require less sideways friction. Keeping the body more directly above the feet also reduces the force needed to maintain balance. A running person asks even more from the ground. Each foot must provide enough grip to accelerate, slow, and redirect the body. Sudden turns require large sideways forces. If the shoes and surface cannot provide them, the foot slips. Athletic footwear is designed around this need. Studs, spikes, rubber compounds, and tread patterns help the foot transfer force without sliding. The exact design depends on the surface. Spikes can press into a track. Studs can push against soil. Soft rubber can conform to indoor flooring. A design that works well on one surface may be poor on another. Static friction also allows vehicles to accelerate. A tyre driven by an engine rotates and pushes backward against the road. If the tyre rolls without skidding, the section touching the road is momentarily at rest relative to the surface. Static friction acts at that contact and pushes the vehicle forward. This can seem strange because the wheel is clearly moving. The important point is that the tyre is rolling. The bottom section touches the road and then lifts away without scraping backward across it. The contact region changes continuously as the wheel turns, but each small part of the tyre is briefly held against the road. When a driver accelerates too hard, the tyre may demand more grip than the road can provide. The contact begins to slide, the wheel spins, and the vehicle may accelerate less effectively even though the engine is working harder. The same principle appears during braking. A rolling tyre can use static friction to slow the vehicle while maintaining controlled contact with the road. If the brakes lock the wheel completely, the tyre slides. Steering becomes more difficult because the contact is no longer able to provide force in the same controlled way. Modern braking systems are designed to prevent prolonged wheel locking. They adjust the braking force so the tyres remain near the limit of grip without entering a continuous skid. The goal is not to avoid friction. The goal is to use the stronger and more controllable grip available before full sliding begins. A parked car on a hill also depends on static friction. The tyres contact the road without sliding. The parking brake and transmission prevent the wheels from rotating freely. The road provides the friction needed to keep the car in place. If the hill is too steep, the road is icy, or the tyres have poor contact, the available static friction may be insufficient. The vehicle can begin to move. Wheel blocks placed behind tyres provide additional security. They do more than add surface friction. Their shape creates a physical obstacle that the wheel must climb. This combines friction with geometry. Ladders offer a more delicate example. Place a ladder against a wall and climb it. The bottom tends to slide outward, while the top tends to move downward. Static friction at the floor and sometimes at the wall helps prevent these motions. The angle matters. A ladder placed too shallowly creates a large outward force at the base. The required friction may exceed what the floor can provide. The condition of the floor matters too. Dust, water, polished surfaces and worn feet can reduce grip. A person climbing changes the load as they move. Higher positions can increase the tendency of the ladder to rotate and slip. This is why secure placement is more important than simply testing the ladder with one foot and deciding that it feels mostly fine. Static friction is also important in knots. A rope wrapped around another rope or a solid post creates many regions of contact. When tension is applied, the rope presses more firmly against the surface. Static friction across the curved contact resists sliding. Additional turns can greatly increase the holding ability because the rope has more contact and the pressure is distributed around a longer path. Sailors, climbers, rescue workers, and builders rely on carefully chosen knots because different arrangements control where friction develops and how loads tighten the structure. A good knot often becomes more secure when pulled because the tension increases contact pressure. A poor knot may roll, loosen, or place stress in an unsafe direction. Shoelaces also depend on static friction. The crossing loops and tightened sections press against one another. Friction keeps the lace from sliding back through the knot. Smooth round laces may loosen more easily than textured flat laces because their contact provides less resistance or because the knot changes shape more readily during movement. Every step bends and shakes the knot. Small forces repeatedly pull at the lace. If those forces cause gradual slipping, the knot eventually comes undone. Static friction can prevent obvious sliding, but tiny local slips may still occur inside a larger contact. A block that appears motionless can experience microscopic movement at some of its contact points. The outer regions may begin to slip while the central regions remain stuck. Stress moves through the contact in a complicated way. As the applied force approaches the maximum grip, more regions can enter partial slip. Final movement begins when the remaining stuck regions can no longer hold the object. This means the change from stillness to sliding is not always perfectly simultaneous across the whole surface. The visible object may remain at rest while parts of the interface are already shifting. Researchers can observe these changes using sensitive instruments and transparent materials. They find that contact failure can spread across a surface like a moving front. One region releases, changing the stress on neighbouring regions. Those regions may then fail. The process can travel rapidly across the interface until the object breaks free. This helps explain why the start of motion can be sudden, even when the applied force increases slowly. The contact network reaches a condition where one small failure triggers many others. A similar process occurs along geological faults. Large regions of rock are pressed together by enormous forces. Tectonic motion tries to move them past one another. Static friction holds sections of the fault in place while stress accumulates. The rocks deform slowly. Some parts of the fault may creep, others remain locked. When the stress exceeds the available grip, slipping can begin in one region and spread. Stored energy is released through the surrounding rock as seismic waves. An earthquake is far more complicated than a box sliding across a floor. Heat, fluids, fractured rock, mineral changes and large variations in pressure all matter. Still, the basic transition from locked contact to sudden motion connects the two situations. Static friction can store the consequences of an applied force. When surfaces remain stuck, the objects around them may deform and store energy. A bent branch, stretched rope, compressed spring, twisted machine part, or stressed rock can all hold energy while friction prevents movement. Once slipping begins, that stored energy can be released quickly. This is why a heavy object tied with a strained rope can jump when the rope slips. It is why a jammed mechanism may move violently when freed. The danger does not come only from the object itself. It comes from energy that accumulated while static friction held everything in place. The same effect appears in smaller and safer experiences. Press a finger sideways against a tabletop without allowing it to slide. The skin stretches. Increase the force and the fingertip deforms more. When the finger finally slips, the skin snaps back toward its usual shape. The motion may happen in short jumps rather than one smooth glide. This can produce a vibration. If repeated, the vibration may create sound. Rub a clean wet finger around the rim of a glass. The fingertip alternates between sticking and slipping. While stuck, it pulls the glass wall slightly. When it slips, the glass vibrates. Repetition keeps the vibration going and produces a tone. A bowed string uses the same transition. Rossin helps the bow grip the string. The string sticks, stretches sideways, then slips back. The cycle repeats rapidly. Music can therefore begin at the boundary between static friction and sliding friction. The grip before slipping is often greater than the resistance after motion has started. This is why a heavy object may be difficult to start moving but easier to keep moving. Before movement, contact junctions have time to form and strengthen. The surfaces settle under the load. Soft material deforms. Adhesive regions grow. Some contaminants are pushed aside. Once sliding begins, junctions are continually formed and broken. They may not have enough time to grow as strong. The contact is constantly disturbed. This does not happen in exactly the same way for every material. In some situations, friction can increase with motion. Rubber, lubricated contacts and soft materials can show more complicated behavior. Still, the common experience of a strong initial grip followed by easier sliding is widespread. Furniture movers often take advantage of it. A heavy cabinet may resist the first push. Once moving, it can continue with less effort, although stopping it in the correct position creates a different challenge. Rocking the cabinet can help start the motion because it changes the load. Tilting one side reduces the contact in some areas. Small movements break static junctions. The object begins moving without requiring every contact point to fail at once. Vibration can produce a similar effect. Shaking a stuck part repeatedly changes the forces at the interface. Individual junctions may break during each cycle. The object can gradually loosen. This is why tapping a jar lid, bolt, or mechanical fitting may help free it. The impact does not simply add a stronger steady force. It sends short stress waves through the materials and disrupts stuck contact regions. Temperature can also change static grip. Heating a metal lid makes it expand. If the lid expands more than the glass jar, the threads or seal may loosen. heat can soften dried material around the rim. It can also reduce the thickness of oils or change moisture at the contact. Cooling can make some materials harder and less able to conform. Others may contract and tighten the fit. The force needed to start motion can therefore depend on what happened before the push. A box that has rested for several hours may be harder to move than one that has just stopped. Over time, microscopic peaks can deform further. Adhesive contacts may grow, soft coatings may settle, moisture may move into or out of the interface. This slow strengthening is sometimes called aging of the contact. It does not mean the objects become old in the ordinary sense. It means the contact network develops while the surfaces remain loaded. The effect is important in machines, tyres, seals, geology and stored materials. A tyre left in one position under a load can develop temporary deformation. A gasket compressed for a long time can change shape. A stack of materials may settle and become harder to shift. Biological contacts can also strengthen with time. The pads on animal feet, the grip of skin and the attachment of cells all involve materials that respond gradually to pressure. Static friction is therefore connected to time as well as force. The speed at which force is applied can matter. A slow push allows materials to deform and contact points to adjust. A sudden impact may break junctions before the load spreads evenly. Pull a tablecloth slowly and dishes may move with it, because static friction has time to accelerate them. Pull the cloth very quickly and the cloth can slide out while the dishes move much less. The familiar demonstration is not proof that friction disappears. Friction acts during the pull, but it acts for a very short time. The dishes receive only a limited change in motion. A slow pull gives friction more time to carry the dishes along. A rapid pull reduces the duration of the interaction. Success also depends on using a smooth cloth, pulling horizontally and avoiding upward movement. Attempting the demonstration with valuable dishes remains an unnecessary way to investigate mechanics. Stacked objects depend on static friction at several interfaces. Place a book on another book and push the lower one gently. If the friction between them is sufficient, the upper book moves along with the lower one. There is no sliding between the books. Push more sharply and the lower book may slide out from beneath the upper one. The required acceleration exceeds the grip at the interface. The same issue affects cargo in vehicles. When a truck accelerates, brakes or turns, unsecured objects rely on static friction with the floor to move with the vehicle. If the needed force exceeds the available grip, the cargo slides. Straps, walls, and restraints are used because friction alone may not be reliable, especially when surfaces are wet, dusty, or uneven. A passenger standing on a bus also depends on static friction. When the bus starts moving, the feet must accelerate with the floor. If the movement is gentle, friction carries the passenger forward. A sudden start may require more grip than the shoes can provide. Even when the feet hold, the upper body initially tends to remain in its earlier state of motion, causing the passenger to lean backward. Holding a rail provides another contact and helps control the movement. In each case, static friction transfers motion between objects. It allows one object to carry another without sliding. Conveyor belts use this effect. The belt moves beneath a package, and static friction accelerates the package until it travels with the belt. Once they have the same speed, the contact can remain fixed relative to the belt. If the package is too heavy, the belt is too smooth, or the acceleration is too sudden, slipping occurs. Designers choose belt materials, textures, and operating speeds to maintain grip. Power transmission belts work similarly. A rotating pulley pulls on a belt. Friction around the curved contact allows the belt to carry force to another pulley. The belt must be tight enough to create pressure, but excessive tension increases wear and loads the bearings. Too little tension allows slipping, heat, and loss of useful motion. Static friction is useful because it can transmit force without continuous rubbing. When the contact holds, there is much less wear than during sliding. A rolling tyre, a gripping belt, and a firmly held tool all benefit from this. No contact is perfectly lossless. materials still deform and tiny regions may slip, yet maintaining static contact usually avoids the intense heating and wear associated with full sliding. This is one reason machines often use rolling elements. A wheel or bearing changes sliding contact into rolling contact. The surfaces can grip momentarily without scraping across one another over long distances. The grip before slipping is not unlimited, and it is not always predictable. Surface contamination can change unexpectedly. Rubber warms, dust collects, water appears, loads shift. Good design includes a margin of safety rather than depending on the exact maximum grip. A ladder is not placed at the steepest angle that worked once. A vehicle should not turn at the higher speed its tyres handled on a dry road. A lifting system should not rely on a knot holding exactly at its estimated limit. The maximum static friction marks the edge of stability. Operating too close to that edge leaves little room for change. The transition becomes especially important when control is needed. Before slipping, forces can be directed through the contact. After slipping starts, the available resistance may fall and the direction of motion can become harder to manage. A shoe begins to slide and balance changes quickly. A tyre begins to skid and steering weakens. A tool slips in the hand and the applied force carries it beyond the intended position. The first movement is therefore not a minor detail. It is change in the way the entire contact behaves. While the surfaces remain fixed together, junctions stretch and support the load. Once they begin moving across one another, those junctions must break repeatedly. Peaks scrape through new regions. Materials deform in a continuous sequence. Where particles can form, heat begins to accumulate more rapidly. The quiet grip gives way to a moving interface, and the energy that was used to overcome the static hold must go somewhere as sliding continues. Once the surfaces begin to slide, the contact changes continuously. The small junctions that held the objects together are pulled apart. New junctions form a short distance ahead, survive briefly, and then break as the movement continues. Surface peaks bend, scrape, and press into new regions. Soft materials change shape. Loose fragments are dragged through the contact. All of this requires energy, and much of that energy eventually appears as heat. This is easy to feel by rubbing your hands together. At first, your palms may be close to room temperature. After several seconds of quick rubbing, they become noticeably warmer. The faster you rub and the more firmly you press, the greater the warming usually becomes. The heat did not appear from nowhere. Your muscles supplied the energy. Chemical processes inside your body allowed the muscles to move your arms and hands. Friction then changed some of that organized movement into irregular motion inside the materials. Atoms in a solid are never perfectly still. They vibrate around their positions. When a surface is heated, those vibrations become more energetic. The warmth in your hands is a sign that the large movement of one palm across the other has been distributed among an enormous number of atoms and molecules. The original motion had a clear direction. Your hands moved back and forth. The microscopic motion produced by friction has no single useful direction. Particles vibrate, twist, and collide in many ways. The energy is still present, but it has become spread out and harder to recover as organized movement. This is why friction is often described as wasting energy. The energy has not been destroyed. It has been changed into a form that may not help us perform the task we intended. A sliding box slows down because its motion is being transferred into microscopic movement within the box, the floor, and the surrounding environment. The surfaces warm slightly. They may also vibrate, make sound, deform, and produce wear particles. If the box is light and the distance is short, the temperature change may be too small to notice. The same process is still happening. The energy is simply spread through too much material to create an obvious rise in temperature. With larger forces or faster movement, the heating becomes easier to detect. Drag a heavy object across a floor, and the contact can become warm. Use sandpaper on wood, and both the sandpaper and the wood heat up. Drill into metal and the drill bit may become too hot to touch. Apply a vehicle brake repeatedly, and the braking components can reach temperatures high enough to damage the materials. The amount of heating depends on how much resistance acts and how far the surfaces slide. Stronger resistance transfers energy more quickly. A longer sliding distance gives the friction more time to act. Speed also matters because rapid sliding can concentrate the energy into a short period. Heat may be produced faster than it can move away from the contact. Rub your hands slowly and the warmth develops gradually. Rub them quickly with the same pressure and the temperature rises sooner. Your muscles are doing work at a faster rate, and friction is converting that energy into heat more rapidly. Pressure changes the heating because it usually changes the true contact area and the strength of the microscopic junctions. Press your hands together more firmly and sliding requires greater effort. More energy is converted during each movement. This does not mean that pressing as hard as possible will always produce unlimited heat. The materials change as they warm. Moisture appears, skin becomes uncomfortable, your muscles become tired. The contact conditions refuse to remain simple for the convenience of the demonstration. A brake system provides a clearer example of frictional heating. When a driver presses the brake pedal, the braking components press against rotating parts connected to the wheels. The friction resists the rotation. The vehicle loses speed, and its organized motion is converted mainly into heat. A moving vehicle contains a large amount of energy because of its mass and speed. Bringing it to rest requires that energy to be transferred somewhere. The brakes, tyres, road, air and mechanical components all receive part of it. During an ordinary stop, the brake discs or drums become warmer. During repeated hard braking, they can become extremely hot. Racing vehicles may produce enough heat for parts of the braking system to glow. The temperature matters because the behavior of the materials changes when they become hot. Brake pads are designed to maintain useful friction across a range of conditions. If they overheat, the friction may fall. The driver presses the pedal, but the vehicle does not slow as effectively. This loss of braking performance is often called brake fade. It can happen when the pad material changes, gases form at the contact, or the braking fluid becomes too hot. Different braking systems fail in different ways, but excessive heat is a common cause. Driving down a long steep hill can create this problem. Holding the brakes continuously converts motion and gravitational energy into heat, without allowing enough time for cooling. Using a lower gear can help because the engine then shares some of the task of controlling the vehicle speed. Brakes are therefore not just devices for producing friction, they are systems for managing heat. They need materials that resist wear, conduct or tolerate high temperatures, and continue working after thousands of heating and cooling cycles. Ventilated brake discs contain spaces that allow air to move through them. Their large exposed surfaces help transfer heat into the surroundings. Racing brakes may use materials that perform well at temperatures where ordinary components would weaken. The design must also avoid removing heat too quickly in an uneven way. Sudden temperature differences can create stress and distortion. A hot disc splashed with cold water may cool unevenly. Repeated expansion and contraction can eventually damage the material. Frictional heating appears in tyres as well, though the process is more complicated than simple sliding. A tyre normally rolls without the entire contact patch scraping across the road. The rubber still deforms as it enters and leaves the contact region. Small areas may slip, especially during acceleration, braking or turning. The rubber also bends around the road texture. These changes produce heat within the tyre. Some warming is useful because rubber often grips better within an appropriate temperature range. Too little heat can leave the tyre stiff and less able to conform to the road. Too much heat can soften it excessively, increase wear, and damage its structure. Racing teams pay close attention to tyre temperature because grip depends on it. The driver may move the vehicle from side to side or accelerate and brake in controlled ways to warm the tyres. The purpose is not merely to make the rubber hot. It is to bring the material into a range where its mechanical behaviour suits the track and conditions. Different rubber compounds have different useful ranges. Ordinary road tyres also warm during use. Long journeys, high speeds, heavy loads, low tyre pressure, and hot weather can increase the temperature. A tyre with too little air bends more with every rotation. The repeated deformation produces additional heat. If the temperature becomes excessive, the internal structure can weaken and fail. This is one reason correct tyre pressure matters. It affects not only comfort and fuel use but also deformation, temperature, wear, and safety. Shoes experience smaller versions of the same process. The sole bends as you walk. It presses against the ground, deforms around texture, and may slip slightly during each step. Energy is lost inside the sole material and at the contact. After a long run, parts of a shoe can feel warm. The runner produces heat through muscle activity, but the materials in the shoe also absorb energy through deformation and friction. A blister is an unfortunate example of repeated frictional effects on skin. The problem is not usually that the skin slides freely across a surface with every step. Different layers of tissue may move slightly relative to one another, while the outer skin is held by the sock or shoe. Repeated shearing stresses damage the tissue. Fluid collects between layers, creating the blister. Heat, moisture, pressure, and repeated motion all influence the process. A well-fitting shoe reduces unwanted movement and spreads pressure more evenly. Socks can manage moisture and provide a controlled layer between the skin and shoe. Lubricants, powders, or protective tape may also change the contact. Reducing a blister to the simple statement that rubbing causes it misses the important details. The damage depends on how the skin is loaded, how often the motion repeats, and whether the tissue can recover. The same is true of wear in machines. When two metal surfaces slide, microscopic junctions form and break. If a junction becomes stronger than the surrounding material, breaking it may tear away a fragment. That fragment can remain attached to the opposite surface or become a loose particle. Loose particles may be carried away by lubricant. They may also remain trapped and scrape both surfaces. A small amount of wear can therefore create conditions for more wear. The contact becomes rougher. Hard fragments cut new grooves. Heat changes the surface layers. Lubricant may become contaminated. The machine can enter a cycle of increasing damage. Engineers inspect used oil partly because it can contain evidence of wear. Metal particles, changes in colour and changes in fluid properties may reveal what is happening inside a machine without requiring immediate disassembly. Filters remove many particles before they return to sensitive contacts. The oil also carries heat away and separates moving surfaces when a stable film can form. In a well-lubricated bearing, the solid surfaces may remain almost completely separated. The movement occurs mainly within the liquid film. Heat is still produced because the liquid resists flowing, but wear can be greatly reduced. If the machine starts after remaining still for a long time, the full protective film may not exist immediately. Some direct contact can occur until the lubricant is distributed. Very low speed, heavy load, or insufficient oil can also allow the surfaces to approach. The contact then moves from fluid resistance toward mixed or dry friction. The transition is important because the amount of wear and heating can change quickly. A machine that seems to be operating normally may become damaged if the lubricating film fails. Lubricants must survive the temperature created by the contact. Excessive heat can make oil thinner, reducing its ability to keep surfaces apart. Very high temperatures can cause chemical breakdown and create deposits. The degraded lubricant then protects the surfaces less effectively, which produces more friction and more heat. The problem can strengthen itself. Cooling systems interrupt this cycle. Engines circulate oil and coolant. Industrial machines may use fans, water, or heat exchangers. Cutting tools often receive a flow of fluid that cools the contact and removes debris. When drilling or cutting metal, friction is only one source of heat. The metal is also being deformed and separated. The tool pushes material aside, creates a chip, and exposes a new surface. Much of the energy used in cutting becomes heat near the tool edge. Without cooling, the tool can soften, lose its shape, or react with the material being cut. A blunt tool often generates more heat because it rubs and deforms the material instead of cutting cleanly. The user may respond by pushing harder, which increases pressure and creates still more heat. The task then becomes slower, precisely because greater effort is being applied in the wrong condition. Replacing or sharpening the tool is usually more effective than continuing a personal disagreement with it. Sawing wood also produces heat. The teeth cut fibers and rub against the sides of the opening. Sawdust can remain trapped and increase resistance. The blade may expand as it warms and begin to bind. A well-designed saw clears material from the cut. The shape and spacing of the teeth create room for sawdust to escape. The blade may also be shaped so that the cut is slightly wider than its main body. This reduces rubbing along the sides and prevents much of the heat that would otherwise develop. Frictional heating can be useful when it is controlled. A match is designed to use a short burst of rubbing to begin a chemical reaction. The match head and striking surface contain materials that respond to heat and abrasion. Dragging the match across the rough strip creates local pressure and rapidly breaks or deforms small regions. Heat develops in a very small area. The temperature rises enough to start reactions that produce still more heat. Once the match ignites, the main energy comes from combustion rather than continued friction. Friction supplies the beginning, not the entire flame. Fire starting with wood follows the same general requirement. Rubbing pieces of wood produces fine material and heat. The heat must accumulate in a small region until the wood begins to react with oxygen. This is difficult because heat continually escapes into the surrounding wood and air. The person must generate it quickly enough and concentrate it effectively. Dry material helps because water absorbs energy and carries heat away as it warms and evaporates. Fine wood dust can ignite more easily than a solid block because it has a large exposed area and requires less energy to heat. The technique is not simply a matter of rubbing harder. Speed, pressure, contact shape, material choice, and heat retention all matter. Friction welding turns this heating effect into an industrial method. Two pieces of material are pressed together while one moves relative to the other. Friction and deformation heat the contact. The material softens without necessarily becoming a freely flowing liquid. The movement then stops, and pressure forges the softened surfaces together. The result can be a strong joint. Different versions use rotation, linear movement, or high-frequency vibration. The exact process depends on the materials and the shapes being joined. This method uses the heat exactly where it is needed. It can join parts quickly, and may avoid some of the additional material required in other welding methods. The surfaces must be controlled carefully. Too little heating produces a weak joint. Too much can damage the material or create an unwanted shape. The heat from friction can also become dangerous when it appears unexpectedly. A bearing that loses lubrication may overheat. A conveyor belt rubbing against a jammed roller can ignite nearby dust or material. A slipping clutch can become hot enough to damage its lining. Industrial environments containing flammable gas, vapor, or fine dust must control possible ignition sources. A hot surface, spark, or overheated contact can begin a fire or explosion. Mechanical sparks are often produced when hard materials strike or scrape. Tiny fragments may be torn away and heated rapidly. If the fragments become hot enough, they glow while moving through the air. The visible spark is not friction turning directly into a beam of light. It is usually a small piece of hot material emitting light because of its temperature, and sometimes reacting with oxygen. Grinding steel creates showers of sparks because the abrasive wheel removes tiny fragments. Their shapes, temperatures, and reactions depend on the metal. Experienced workers can sometimes distinguish materials by the appearance of the sparks, though proper testing is more dependable than making important decisions from an especially dramatic shower. Friction can produce electricity as well as heat. When different materials touch and separate, electrons may transfer from one surface to the other. Repeated rubbing can increase this charge separation. Walk across a carpet in dry air, and your body may collect electric charge. Touch a metal object and the charge moves suddenly, producing a small spark and a sharp sensation. The rubbing does not create electric charge from nothing. It helps transfer and separate charge that was already part of the materials. Dry air allows the charge to remain for longer because moisture usually helps it leak away. This is why static shocks are often more common in dry conditions. Although this is called static electricity, the word static refers to charge accumulating rather than to static friction. The two effects can occur together during rubbing, but they describe different things. Heat can change friction while friction is producing heat. This feedback makes sliding behavior complicated. A block sliding slowly may have one level of resistance. As the surface is warm, one material may soften. The true contact area may grow, increasing friction. In another situation, heat may melt or release a thin layer that acts as a lubricant, reducing friction. A surface coating may break down, moisture may evaporate, oil may become thinner. The resistance can rise, fall, or vary irregularly as the temperature changes. Snow and ice provide useful examples. Sliding skis generate some heat at the contact, but pressure, surface structure, temperature, and water layers also matter. A very thin layer of water can reduce resistance and allow easier sliding. Too much water can create drag. At very low temperatures, the snow may remain dry and abrasive. Near melting conditions, the contact behaves differently. Ski bases use materials and textures chosen for particular snow conditions. Wax changes the interaction between the base, ice crystals, water, and dirt. The best surface is not always the smoothest possible one. Fine grooves can help manage water and reduce suction. The correct choice depends on temperature and snow structure. Ice skating also involves a narrow metal blade pressing against ice. The blade creates high local pressure, and frictional heating occurs during movement. The surface of ice already has unusual molecular mobility, and the contact can involve a thin lubricating layer. The simple explanation that the blade melts the ice entirely through pressure is not enough. Several effects contribute, and their importance changes with temperature and speed. What the skater experiences as a smooth glide is the result of a carefully shaped blade interacting with a complex surface. The blade must still grip sideways when the skater pushes. Its edge presses into the ice, allowing force to be transferred. Smooth forward motion and controlled sideways resistance are both required. Too much grip would make gliding difficult. Too little would make pushing and turning impossible. This balance appears in many systems. We rarely want the smallest possible friction everywhere. We want the right amount in the right direction and under the right conditions. A pencil depends on sliding friction to leave a mark. As the graphite-based core moves across paper, the rough paper removes small flakes. Those flakes remain attached to the fibers and form the visible line. A softer pencil transfers more material and usually creates a darker mark. A harder pencil leaves less material and can make a finer, lighter line. The writing process slowly wears the pencil point and may warm the contact slightly, though the heat is too small to matter. The useful result is material transfer caused by controlled friction and wear. An eraser uses a related process. The soft eraser grips graphite particles and pulls them from the paper. Small pieces of the eraser itself break away, carrying some of the graphite with them. The crumbs left on the page are evidence that the eraser is designed to wear. A material that never changed might not remove the mark as effectively. Cleaning often relies on controlled friction. A cloth rubbed across a surface catches dust, oils, and loose material. Scrubbing applies repeated shear forces to deposits. Soap and water change the chemistry and reduce adhesion, while the cloth provides movement and contact. A rough sponge can remove stubborn material by increasing local pressure and abrasion. Too much friction damages the surface being cleaned. Paint becomes dull. Plastic scratches. Fabric fibers weaken. The useful range lies between failing to remove the dirt and removing part of the object along with it. Polishing also uses friction and abrasion, but the goal is to make surface irregularities smaller. Fine particles remove raised regions and reduce the depth of scratches. As polishing continues, progressively finer abrasives may be used. The surface begins to reflect light more evenly because its remaining irregularities are small. The surface is not made perfectly flat, it is made smooth enough at the relevant scale. Polishing creates heat, so speed and pressure must be controlled. Excessive heat can soften coatings, distort plastics, or change the colour of metals. The worker may use liquid to cool the surface and carry away removed material. Once again, successful friction depends on managing heat, wear, and contamination together. On a much larger scale, friction affects moving rock, soil, glaciers, and landslides. When a mass of material slides downhill, friction resists the motion and produces heat. In a slow movement, the heat may spread into the environment without a dramatic temperature rise. During rapid movement under high pressure, local temperatures can become much greater. Rock surfaces may fracture, crush, and sometimes develop thin altered layers. Water can reduce resistance by increasing pressure within soil or rock, and by separating grains. It can also increase cohesion in some partly wet materials. The outcome depends on how much water is present and where it moves. A landslide may begin when gravity overcomes the available grip along a weakened region. Once sliding starts, crushed material and rising pressure can reduce resistance further. The movement accelerates. This resembles the smaller transition from static to sliding friction, but the materials are uneven, changing, and spread across a large area. At every scale, sliding converts some organised motion into heat. The amount may be tiny or enormous. The heat may be useful, harmless, wasteful, or dangerous. It may warm a hand, stop a car, light a match, join metal, damage a bearing, soften a tyre, or alter a geological fault. The basic process begins at the moving contact. Junctions are created and broken. Materials are deformed. Peaks scrape through surfaces. Internal structures vibrate and rearrange. Energy enters through the movement and spreads among microscopic motions. The temperature reached depends on more than the total energy. It depends on how quickly the energy arrives, how small the heated region is, how well the materials conduct heat, and how quickly cooling occurs. Metal often conducts heat away from the contact more effectively than wood or rubber. A metal object may spread the energy through a large volume. The surface might not become as locally hot, though the heat can reach other components. Rubber and many plastics conduct heat poorly. Energy can remain concentrated near the contact. The material may soften, smear, or degrade. A short rapid slide can create a very hot microscopic region even when the average temperature of the object remains low. Some contact points may experience conditions very different from what a nearby thermometer would report. This local heating can change the surface chemistry. Oxide layers form, lubricants react, polymers break down, material becomes harder or softer. The next moment of sliding then occurs on a surface that is no longer quite the same as before. Friction changes the contact that creates it. Sliding smooths some regions and roughens others. It removes material and deposits fragments elsewhere. It heats surfaces and alters their properties. This is why friction can evolve during use. A new brake pad behaves differently after it has settled against the disc. A fresh shoe sole changes after walking. A machine may become smoother during early operation and rougher later as wear accumulates. Controlling sliding friction means controlling this entire changing system. Sometimes we increase the pressure to gain stronger braking or grip. Sometimes we reduce pressure to protect delicate surfaces. We add tread when water must be moved. We polish when sharp peaks cause damage. We apply oil when direct contact must be prevented. We choose soft materials when close contact is useful, and hard materials when wear must be limited. None of these choices works in every situation. The same oil that protects an engine would be dangerous on a brake disc. The rubber that grips a road would be inefficient inside a high-speed bearing. The roughness that helps a shoe on soil may scratch a polished floor. Useful friction is not simply high friction, and efficient movement is not simply low friction. The correct contact depends on the task. To choose that contact, we need to look more closely at the factors that change the grip. The materials themselves matter, but so do weight, pressure, temperature, speed, surface films, and the way lubrication separates one moving surface from another. The amount of grip between two surfaces can change so much that it may seem as though friction is behaving inconsistently. A rubber shoe can hold firmly on dry pavement and slide across wet tile. A metal drawer can move easily after oil is applied, while the same oil on a staircase would create an immediate problem. A heavy box is usually harder to push than a light one, yet a larger visible contact area does not always create more resistance. These differences make sense once the materials, the load, and everything present between the surfaces are considered together. The materials decide how the contact points form and how those points respond when a force is applied. A hard material may keep its general shape while its smaller surface peaks carry the load. A softer material may spread across the opposing surface and create a much larger true contact area. A brittle material may crack. A flexible one may stretch. A sticky material may form strong adhesive contacts. A layered material may allow movement within itself. This is why no material has one permanent amount of friction. Rubber does not always have high friction, and metal does not always have low friction. The result depends on what each material touches and the condition of the contact. Rubber often provides strong grip because it is flexible enough to conform to small surface features. Press it against a road, a floor, or a piece of glass, and it can spread into microscopic valleys that a harder material would bridge over. This close contact allows attractive forces to act across many regions. Rubber also loses energy when it changes shape. As it is pulled over a rough surface, it bends around each feature. The material does not spring back with perfect efficiency. Some of the energy becomes heat, increasing the resistance to motion. Both effects can contribute at the same time. The rubber adheres to the surface while also deforming around its texture. The exact balance depends on the type of rubber. Some rubber compounds are soft and sticky. Others are harder and designed to resist wear. A soft compound may provide excellent grip but lose material quickly. A harder compound may last longer while offering less grip under certain conditions. Tire manufacturers, shoe designers, and makers of industrial belts choose mixtures according to the task. They adjust the kinds of rubber, fillers, oils, and other ingredients used in the material. The finished product must remain useful across a range of temperatures, speeds, and loads. A racing tyre may be designed for strong grip during a short period of intense use. A road tyre must survive thousands of journeys, changing weather, rough surfaces, and long periods of storage. A shoe sole must bend comfortably, resist wear, grip the floor, and avoid leaving marks. One rubber cannot do all of these jobs equally well. Metal behaves differently because it is usually much stiffer. The visible shape changes very little under ordinary loads, but the microscopic peaks can still deform. At the true contact points, pressure may become high enough to flatten small regions or create adhesive junctions. Clean metals can grip strongly because atoms from opposing surfaces may bond at close contact points. Oxide layers, oils, and contamination normally reduce this effect, but they do not remove it completely. When metal slides against metal without lubrication, those junctions can tear apart. Material may transfer from one surface to the other. The contact becomes rougher, heat increases, and wear accelerates. Some pairs of metals are more likely to stick than others. Similar materials may form strong junctions because their atomic structures and chemistry are compatible. Engineers sometimes choose different materials or apply coatings to reduce this tendency. A hard steel shaft may run inside a bearing made from a softer metal or a specially designed composite. The softer material can adjust to small imperfections and may trap harmful particles away from the shaft. The materials are chosen as a pair rather than independently. Ceramics can be extremely hard and resistant to high temperatures. They may produce low wear under suitable conditions, but they can also be brittle. A sharp impact or concentrated stress may create cracks. Some ceramics are used in bearings, cutting tools and brakes because they remain stable where metals might soften. Their friction still depends on surface finish, load, temperature, and any lubricant present. Plastics cover a very wide range of behaviour. Some are soft and adhesive, others are hard and slippery. Certain plastics contain long molecular chains that can move past one another relatively easily, giving them low friction against many surfaces. These low-friction plastics are used in guides, seals, bearings, and sliding components. They may operate with little or no liquid lubrication, which is useful in places where oil would attract dirt or contaminate a product. Other plastics soften under heat and can smear across the opposing surface. A thin transfer layer may form, changing the contact. Sometimes this reduces friction. Sometimes it increases wear and creates irregular movement. Wood has its own complications. Its surface is made of fibres arranged according to the grain. Sliding along the grain can feel different from sliding across it. Moisture changes the stiffness and size of the fibres. Finishes, waxes and oils alter the outer layer. Fresh rough wood may produce strong resistance because fibres bend, break and catch. Polished wood can slide more easily, but a sticky finish may increase grip. Dust from wear can act as a loose layer between surfaces. Paper is also fibrous. A sheet may slide easily across a polished desk but grip another sheet of paper more strongly. The fibres and coatings interact, and static electrical charge can add attraction in dry conditions. Fabric depends on weave, fibre type, surface hairs, tension, and direction. A soft fabric may conform closely to skin. A smooth synthetic fabric may slide easily. A rough weave can catch on an opposing texture. Two fabrics may grip strongly because their fibres interlock, even if each one moves easily across a hard surface. This is one reason clothing layers can behave differently depending on the materials worn together. Skin changes more than most manufactured surfaces. It is soft, elastic, ridged, slightly oily, and often moist. Its properties vary from one part of the body to another, and from one moment to the next. Dry skin may make limited contact with smooth objects. A small amount of moisture can soften the outer layer and improve grip. Greater moisture may create a liquid film and reduce grip, especially on a smooth surface. Sweating can therefore help or hinder. During climbing or weightlifting, moisture may make the hands slippery. Chalk is used to absorb water and increase the reliability of the contact. It does not simply make the hand rougher, it changes the moisture and the way the skin meets the surface. Gymnasts, climbers and lifters use different chalk products and application methods because too much loose powder can also reduce contact. The useful amount depends on the person, the equipment and the environment. Rosin works differently. It is used by musicians, dancers and some athletes because it increases adhesion. A violin bow needs enough grip to pull the string before slipping. A dancer may use rosin on footwear to improve traction on a stage. The same substance that improves one contact would be unsuitable inside a bearing. Whether a material is helpful depends entirely on what the movement requires. Weight changes friction mainly by changing how strongly the surfaces are pressed together. A heavier object pushes more firmly against the supporting surface. The microscopic peaks carry greater loads, flatten more, and create a larger true contact area. More contact points can form, and existing junctions can become stronger. Greater force is then needed to begin or maintain sliding. This is why adding books to a box usually makes the box harder to push. The floor has not changed, and the visible base of the box remains the same. The contact has become more heavily loaded. The relationship is often close enough to direct that doubling the load roughly doubles the friction in many simple dry contacts. This is a useful approximation, but real materials can depart from it. Soft rubber may spread in a more complicated way. A surface coating may break under increased pressure. A lubricant may be squeezed out. Loose particles may become embedded. A material can become warmer or change shape. At very high loads, permanent damage may begin. Peaks flatten completely. Grooves form. Surfaces crack. The friction can rise or fall depending on what the damage creates. The way the force is applied matters as much as the total weight. Push downward on a box while trying to move it, and the contact load increases. Pull upward at an angle, and part of the pulling force reduces the load on the floor. The box may become easier to slide. This is why pulling a suitcase or trolley by an angled handle can feel easier than pushing downward on it. The handle changes both the direction of motion and the pressure at the contact. Push a broom at a steep downward angle, and the head presses more firmly against the floor. Friction increases. Pull the broom toward you, and the handle may lift the head slightly, reducing the load. The same tool can therefore feel different depending on which direction it is moved. Clamps use pressure to create grip. Tightening a clamp presses surfaces together, increasing the available static friction. A workpiece can then remain fixed while it is cut, drilled or shaped. A clamp must provide enough pressure to resist the working forces, but excessive pressure can damage soft material or distort the object. Protective pads spread the load and reduce marking. A vise holds material in the same way. The jaws may have textured faces to increase grip, but the clamping force is equally important. Soft jaw covers can protect delicate surfaces while creating close contact. Knots also turn tension into pressure. As a rope tightens around another object, it presses more firmly against the contact. Friction increases and prevents slipping. The shape of the knot directs the forces so that pulling can make the contact more secure. Different rope materials affect the result. A smooth synthetic rope may require a different knot from a rough natural fibre rope. The stiffness of the rope matters too. A flexible rope wraps closely and creates a longer contact. A stiff rope may resist bending and leave sections with lower pressure. Weight affects tyres in a more complex way. A heavier vehicle presses the tyres more firmly against the road and can create greater total grip. The contact patch grows and the rubber deforms more. However, the grip does not always increase in perfect proportion to the load. Tyres can become less efficient at producing grip for each added amount of weight. Temperature and pressure change, and the rubber may operate in a less favourable condition. This is why moving weight around a vehicle affects handling. During braking, weight shifts toward the front tyres. They are pressed more firmly against the road and can provide more braking force. The rear tyres carry less load and can lose grip more easily. During acceleration, weight may shift toward the rear. During a turn, the outer tyres carry more load than the inner tyres. Suspension systems are designed partly to manage these changes. Keeping the tyres in useful contact with the road allows their available friction to be used more effectively. Adding weight does not automatically make a vehicle safer. A heavier vehicle has more motion to control and requires greater forces to accelerate, turn and stop. Although tyre grip can increase, the demands on the tyres also increase. The extra load may raise tyre temperature and braking temperature. It can increase wear and change the response of the suspension. Weight and grip must be considered together with the movement being attempted. Lubrication changes the contact by placing another material between the surfaces. Instead of two solids pressing directly against one another, they may be partly or completely separated by a layer of oil, grease, water, powder, or another substance. The purpose is often to reduce friction and wear, but a lubricant does not simply make everything slippery in the same way. A thick liquid resists movement within itself. Honey is harder to stir than water because its layers do not slide past one another as easily. An oil can reduce direct solid contact while still creating resistance as it flows. The best lubricant provides enough separation without producing excessive drag. Viscosity describes how strongly a fluid resists flowing. A high viscosity oil is thicker and usually forms a stronger film under load. It may also create greater resistance. especially when cold. A low viscosity oil flows easily and creates less drag. It may be unable to keep heavily loaded surfaces apart, particularly at low speed or high temperature. Choosing a lubricant means balancing these needs. The correct oil for a small fast mechanism may be unsuitable for a heavily loaded gearbox. An engine operating in cold weather faces different conditions from one working at high temperature. Manufacturers specify particular lubricants because the machine was designed around their behaviour. Replacing them with whatever liquid happens to be nearby is not an experiment that most mechanical systems appreciate. Temperature strongly changes viscosity. Most oils become thinner as they warm. At startup, cold oil may move slowly and create high resistance. As the machine reaches its working temperature, the oil flows more easily. If it becomes too hot, the film may become too thin. The surfaces approach one another and direct contact increases. Modern oils often contain additives that reduce the amount their viscosity changes with temperature. Other additives protect against oxidation, prevent foam, control deposits, and reduce wear. Some additives attach to metal surfaces and create molecular layers. These layers can reduce adhesion when the main liquid film becomes very thin. Under extreme pressure, special additives may react with the surface and form protective compounds. The reaction sacrifices a very thin layer to prevent more serious damage beneath it. Grease is oil held within a thickening structure. It remains in place better than liquid oil and can seal out some contamination. It is useful in bearings, hinges, and joints, where continuous oil circulation is impractical. Grease does not behave like a solid plug. During movement, it releases oil into the contact and shifts within the component. The thickener helps keep the lubricant where it is needed. Too much grease can create extra resistance and heat. It may churn as parts move, wasting energy. Too little leaves areas unprotected. Applying more lubricant is not always better. Water can act as a lubricant, but its effects depend heavily on the surfaces. A small amount of water between rubber and a smooth floor may reduce grip by separating the materials. On rough pavement, tyre tread can move much of the water away and preserve contact. If water builds faster than it can escape, a tyre may ride on a layer of liquid. Direct contact with the road falls sharply, and steering or braking becomes difficult. Speed increases the risk because the water has less time to move away. Deeper water and worn tread make the problem worse. Vehicle weight and tyre pressure also influence how the contact develops. Water on skin can increase or decrease friction. Slightly damp skin may grip glass more strongly. Very wet skin can slide more easily because a continuous film forms. After long exposure, skin absorbs water and softens. Its ridges swell, and its resistance to damage changes. A wet hand may grip one object well while becoming more vulnerable to rubbing injury. Soap reduces friction by changing the interaction between water, oils, and surfaces. Soap molecules help water spread and surround greasy material. The resulting layer allows hands or objects to slide more easily. This is useful for washing and dangerous when stepping into a bath. The soap has no awareness of context. Dry lubricants are used where liquid would be unsuitable. Graphite consists of carbon atoms arranged in layers that can move over one another relatively easily. Fine graphite powder can reduce friction in locks and some mechanisms. Certain other solid materials have similarly low resistance between internal layers. They may be used as powders, coatings, or ingredients in composite parts. A dry lubricant does not attract dirt in quite the same way as sticky oil, though powders can still migrate or become contaminated. Some work well in vacuum or at temperatures where ordinary oils would fail. Air itself can provide lubrication. An air bearing uses a thin, pressurized layer of gas to separate surfaces. With almost no direct contact, movement can be very smooth. Such bearings are used in precision equipment where tiny irregularities would cause unwanted vibration. They require clean surfaces and a reliable air supply. A loss of pressure can bring the solids into contact suddenly. Water bearings and magnetic systems can also reduce direct contact. The goal is the same: support the load while allowing movement without repeated solid rubbing. Complete separation is not always possible. Many contacts operate in a mixed condition. Part of the load is carried by the lubricant film, while microscopic peaks still touch. At low speed, the film may be thin, and solid contact may dominate. As speed increases, movement can draw more lubricant into the gap and create stronger separation. This is why some machines experience greater wear during startup and shutdown than during steady operation. Once moving at the intended speed, they create a stable film that protects the surfaces. A door hinge works under simpler conditions. A small amount of oil enters the gap between the pin and the surrounding metal. It reduces adhesion and allows the parts to slide with less resistance. Oil may also quiet the hinge because it changes the sticking and slipping that cause the squeak. The sound disappears when the movement becomes smoother. Eventually, dust and wear particles may collect in the oil. The lubricant can dry, leak away, or become thick. The squeak returns, usually at a time when quiet movement would have been especially helpful. Lubrication can increase grip in some situations rather than reduce it. Certain sticky materials are applied to belts or sports equipment to improve adhesion. A thin liquid layer can create suction or capillary attraction between smooth surfaces. Very thick fluids can transmit force between moving parts. Automatic transmissions and hydraulic systems use liquids to carry energy. The fluid resists rapid movement and creates controlled coupling. The word lubricant therefore describes a role more than one universal effect. A substance that reduces harmful solid contact may still produce useful resistance within itself. Surface coatings offer another way to change friction. A hard coating can protect a softer material from wear. A low-friction coating can reduce adhesion. A textured coating can increase grip. The coating may be only a very thin layer, yet it controls the contact because friction begins at the surface. Paint changes the grip of metal, wood, or concrete. A glossy coating may be easier to clean but more slippery. A rough coating may provide traction but collect dirt. Non-slip floors often contain hard particles that create stable texture. The particles must remain attached. Loose grit can behave like small rollers and make the floor less secure. Wax can reduce friction by filling small irregularities and forming a layer that shears easily. It is used on skis, furniture, floors, and tools, though the desired effect differs in each case. A waxed ski should glide. A waxed wooden drawer should move without sticking. A waxed floor may shine beautifully while making everyone walk with unnecessary concentration. On some sports surfaces, wax or resin is used to increase grip rather than reduce it. Again, the result depends on the materials and the thickness of the layer. Contamination can behave like accidental lubrication. Oil from skin, food residue, cleaning products, dust, and moisture all alter surfaces. A handle that was secure when clean may become slippery after contact with oil. A brake disc contaminated with grease can lose much of its useful friction. A belt may slip because a leaking lubricant has reached it. In other cases, contamination increases resistance. Sticky residue can make a drawer difficult to move. Fine particles can become trapped and scratch the surfaces. Corrosion creates rough products that interfere with motion. Rust on a bolt does more than make the surface rough. Corrosion products occupy space, bind the threads, and alter the metal. Water and oxygen continue to react within the contact. Penetrating oil helps by moving into small gaps, reducing adhesion, and carrying lubricating material between the threads. Time allows the oil to spread. Vibration or tapping may break the corrosion bonds. The load on the threads remains important. A bolt tightened strongly presses its surfaces together. Even after lubrication, substantial force may be needed to begin movement. Temperature can assist because the parts expand by different amounts. Heating one component may increase the gap. Cooling another may shrink it. The successful removal of a stuck bolt may involve material, weight, lubrication, temperature, and impact all at once. Pressure can squeeze lubricant away. Place a thin layer of oil between two heavily loaded surfaces, and the liquid tries to escape from the contact. If the movement is too slow to draw more oil in, the surfaces may approach until only a molecular film remains. Grease stays in place more effectively, but even grease can be displaced. Seals, grooves, and reservoirs help maintain the supply. Some surfaces are designed with tiny pockets that hold lubricant. These pockets release fluid during movement and collect wear particles. A surface that appears slightly rough may support lubrication better than one polished to the greatest possible smoothness. This is another reason smoothness alone does not guarantee low friction. The shape of the contact affects how a lubricant behaves. A rotating shaft can pull oil into a narrowing gap and build pressure within the fluid. That pressure supports the load and separates the surfaces. The parts may appear to be touching, but during normal operation the shaft can ride on the oil film. If speed falls, the supporting pressure decreases and contact becomes more likely. Bearings are designed with carefully chosen clearances. Too much space allows unwanted movement and weakens the fluid film. Too little space restricts oil flow and may create heat. The correct gap can be much smaller than anything visible without measuring equipment. Human joints use their own forms of lubrication. The ends of bones are covered by smooth cartilage, and fluid within the joint reduces resistance. The cartilage deforms under load and helps distribute pressure. Movement can assist the circulation of fluid through the contact. The joint combines low friction, load support, and the ability to withstand repeated use. Damage to cartilage changes this balance. The surfaces become rougher, pressure distribution worsens, and movement may become painful. Biological repair is limited, making the protection of these contacts especially important. The eye also depends on lubrication. Tears spread across the surface as the eyelid moves. The liquid reduces rubbing, removes particles, and maintains a suitable optical surface. When the tear film is insufficient or unstable, blinking can become uncomfortable. A movement performed thousands of times each day suddenly becomes noticeable because lubrication has failed. Saliva performs a related role in the mouth. It reduces friction during chewing and swallowing, protects tissue, and helps food move. A dry mouth changes speech and eating because surfaces that normally slide begin to drag. Living systems use liquids wherever repeated contact must remain gentle. Materials can be designed to supply their own lubrication. Some bearings contain oil within pores. As the bearing warms, small amounts of lubricant move toward the surface. When it cools, some can return into the material. Composite parts may contain solid lubricating particles throughout their structure. As the surface wears, new particles are exposed. The low friction property is not limited to one fragile coating. These designs are useful where regular maintenance is difficult. They still have operating limits. Excessive load can crush the material. High speed can create too much heat. Dirt can enter the contact. A self-lubricating part is not free from every possible mechanical problem. The amount of grip is therefore a result of several connected choices. The material controls stiffness, adhesion, deformation, and wear. The load controls pressure and true contact area. The lubricant controls separation, flow, and surface chemistry. Temperature changes the materials and the lubricant. Speed changes deformation and film formation. Time allows contacts to strengthen or fluids to move. Dirt, water, and wear particles alter the interface. No single factor works alone. A soft material under light pressure may grip gently. The same material under a heavy load may spread, heat, and wear. A thick oil may protect a slow heavy mechanism, but waste energy in a fast light one. A rough surface may provide traction when dry, and trap a slippery film when wet. The best contact is designed for the actual situation, rather than for a simple goal of maximum or minimum friction. This becomes clear when we look at where friction is used every day. feet need enough grip to start, stop and balance on changing ground. Tyres must transfer engine, braking and steering forces while surviving heat and wear. Machines must keep some contacts nearly frictionless, while making others hold firmly. Animals and plants use claws, pads, hairs, scales, and surface coatings to control their contact with the environment. The same basic interactions appear in all of them, but each system arranges its materials, pressure, and surface conditions in a different way. All of those choices become easier to understand when we look at the places where friction is doing practical work. Feet, tyres, machines, and living organisms all face the same basic problem. They must press against something, transfer force through the contact, and avoid slipping at the wrong moment. The human foot is a good place to begin because walking feels effortless until the available grip changes. On a dry floor, most people can stand, turn, accelerate, and stop without thinking about the forces involved. The sole of the foot presses downward, the ground supports the body, and friction acts along the surface whenever balance or movement requires it. During a normal step, the heel often meets the ground first. The rest of the foot then lowers, carries the body, and pushes backward before leaving the surface. The forces at the contact change throughout this movement. The foot does not simply press straight down, it also pushes forward, backward, and sideways in small amounts. Static friction prevents the sole from sliding while these forces are transferred. Balance depends on constant adjustment. The body is never perfectly still, even when a person appears to be standing quietly. Muscles make small corrections. Weight shifts between the heels, toes, and sides of the feet. Friction allows these corrections to produce useful forces against the floor. Without enough grip, the corrections stop working as intended. A small sideways push causes the foot to move instead of the body. The nervous system detects the change and responds by shortening steps, slowing movement, and placing the feet more carefully. Bare feet can grip many surfaces well because skin is soft and able to conform to small irregularities. The toes also help control pressure and balance. Their movement changes the shape of the contact and allows the foot to adjust to uneven ground. On natural surfaces, the foot may press into soil, sand, grass, or rock. The ground itself can deform. Grip then depends not only on friction at the skin or shoe, but also on the strength of the surface beneath it. A foot on firm soil can push backward because the soil resists being displaced. On loose sand, the grains move. Energy is spent rearranging them, and the foot may sink or slide. Walking becomes harder because each step changes the surface that must provide support. A shoe gives the foot a new contact material. Its sole can be designed for particular conditions. Soft rubber may grip smooth, dry surfaces. Deep tread can press into mud. Small edges can catch against rock texture. Studs can penetrate soil or artificial turf. The shape of the tread matters because different surfaces fail in different ways. On wet pavement, grooves give water space to escape. On soft ground, widely separated lugs can push against the soil. On snow, many small edges can grip compressed crystals. On indoor flooring, a broad, soft sole may create better contact than a deep outdoor tread. A sole that works well in one place may perform poorly somewhere else. Hiking boots can be secure on loose trails yet awkward on polished stone. Smooth climbing shoes can grip rock well through close rubber contact, but offer little support in deep mud. Footwear also has to manage wear. A very soft sole may provide strong grip but lose material quickly. A very hard sole may last longer, but fail to conform to the ground. Designers adjust hardness across different regions. The heel may need resistance to repeated impact. The front must bend during walking. The edges may require support during turns. The tread must remain useful after part of it has worn away. Temperature changes the sole. Rubber can become harder in cold conditions and softer when warm. A shoe that grips well indoors may behave differently outside in winter. Contamination matters just as much. Dust can settle between the sole and floor. Mud can fill the tread until the pattern no longer reaches firm ground. Oil can create a thin layer that prevents direct contact. This is why cleaning a shoe or wiping a floor can restore grip without changing either main material. The important change occurs in the layer between them. The same principles apply to animal feet, though nature uses a much wider range of designs. Cats use soft pads that conform to surfaces and claws that can press into softer material. The pads provide quiet contact and useful grip on floors, branches, and rock. The claws add mechanical support when the surface allows penetration. A claw does not rely only on friction. It creates an obstacle against slipping by, hooking into the material. This is useful on bark and soil, but less effective on hard, smooth glass. Dogs also use pads and claws. Their grip changes with the condition of the pads, the length of the claws, and the surface beneath them. On ice, the hard claws may scratch without gaining enough purchase, while the pads can slide on the thin surface layer. Hoofed animals use a different arrangement. A hoof supports weight through a hard outer structure. Its shape allows the animal to press into soil and uneven ground. Some hooves spread slightly under load, increasing stability. Mountain goats have hooves with firm outer edges and softer inner pads. The edges can catch on small rock features while the pads conform to the surface. This combination provides support on steep terrain. Horseshoes change the contact between hoof and ground. Different shapes, materials, and added features are used for roads, soil, snow, and sport. The shoe must protect the hoof while still providing appropriate traction. Too little grip is dangerous, but too much can also be harmful. If a hoof catches strongly while the body continues moving, large stresses can reach the leg. The best contact allows control without preventing every small adjustment. Bird feet are shaped for their usual environment. Perching birds wrap their toes around branches. The curved contact and tendon arrangement help maintain a grip without constant muscular effort. Birds that walk on mud may have long spreading toes that distribute weight. Birds that swim have webbed feet designed more for pushing water than gripping solid ground. Birds of prey use sharp talons to penetrate and hold. Geckos solve the problem without claws or sticky liquid on many surfaces. Their toes carry extremely fine structures that divide into smaller branches. These structures create close contact with the surface. Weak molecular attractions act across the many contact points. Together, they provide enough force to support the animal. The gecko controls the grip by changing the angle of the toe structures, allowing attachment and release during each step. The contact is strong in the required direction but can be removed quickly. That is essential. A foot that attaches securely but cannot release would make climbing a very short activity. Insects use hairs, hooks, pads, and small amounts of fluid. A fly can walk on glass because its feet form close contact and use surface forces that are powerful compared with its low weight. Small size changes the balance of forces. An insect weighs very little, so molecular attraction and surface tension can support it more easily than they could support a large animal. Some insects secrete thin liquids that improve contact on smooth surfaces. The liquid can create capillary forces and help the foot conform. The amount must be controlled so the insect can still detach its foot. Spiders use fine hairs that create close contact and directional grip. Many can move across walls or ceilings by engaging large numbers of tiny structures. These biological systems have inspired artificial gripping materials. Engineers study how fine hairs, flexible pads, and directional structures can produce strong attachment without ordinary glue. Artificial versions may be useful for climbing robots, manufacturing tools, medical devices, and equipment that handles delicate objects. The challenge is to keep the surface clean and maintain reliable contact after repeated use. Snakes use friction in another way. Their bodies press against the ground over a long contact area. Scales interact differently with the surface depending on direction. Muscles push parts of the body sideways or backward, and the ground provides the reaction needed for forward movement. On a perfectly smooth surface with very little grip, a snake may struggle to move because its body cannot push effectively against the environment. Different forms of snake movement suit different ground conditions. Some depend on bends in the body pressing against stones or plants. Others use the edges of the scales to resist backward slipping. Worms move through soil by changing the shape of their bodies and using small bristles to anchor sections. One part grips while another extends or contracts. Movement depends on alternating attachment and release. The pattern resembles walking in a simple form. A contact holds long enough to transfer force, then releases so the next movement can occur. Tyres face the same requirement at much greater speed and under much heavier loads. A tyre must support the vehicle, roll with limited energy loss, absorb road irregularities, survive heat, resist wear, and provide grip for acceleration, braking and turning. These demands compete with one another. A soft tyre may grip well but wear quickly and waste more energy through deformation. A hard tyre may last longer but provide less grip on some surfaces. The tread pattern manages water, loose material and deformation. Grooves divide the contact into blocks. Those blocks bend as they enter and leave the road. Their edges can interact with surface texture, but excessive movement creates heat and uneven wear. On a clean, dry road, the rubber can make close contact with the pavement. The road may look rough, but the tyre deforms around many of its small features. Adhesion and internal deformation both contribute to grip. When rain falls, water enters the contact. The tread must move it aside. If the water cannot escape quickly enough, the tyre loses direct contact with the road. At high speed, the front of the tyre pushes against the water and can begin to rise onto a liquid layer. Steering and braking forces then fall sharply. Worn tread increases the risk because the grooves hold and move less water. Deep water makes the problem worse, as does speed. Slowing down helps because it gives water more time to move out of the contact. It also reduces the grip required for sudden changes in motion. Snow presents a different problem. A tyre can compress snow into the tread. Snow sometimes grips snow better than rubber grips snow, so retaining a controlled amount within the tread can help. Winter tyres use compounds that remain flexible in cold conditions. They often contain many small cuts that create extra edges and allow the tread blocks to deform around the surface. A summer tyre may become too hard in cold weather, reducing its ability to conform. The problem is not limited to visible snow or ice. Low temperature alone can change the material. Studded tyres use hard points that press into ice. They gain mechanical support by scratching and penetrating the surface. They can improve grip in certain winter conditions, but may damage roads and perform differently on dry pavement. Racing tyres are chosen for narrow operating conditions. Dry tyres may have little tread to maximise rubber contact. Wet tyres contain grooves to clear water. Teams monitor temperature because the rubber needs to remain within a useful range. A tyre that is too cold may lack grip. One that is too hot may soften, wear rapidly, and lose performance. The driver controls tyre friction through steering, braking, and acceleration. Smooth movements keep the required forces within the available grip. Sudden inputs can exceed it. During a turn, the tyres must provide sideways force. During braking, they provide force opposite the motion. Asking for strong turning and strong braking at the same time places a greater demand on the contact. If that demand becomes too large, the tyre slides. Once sliding begins, control can decrease and heat rises quickly at the contact. Anti-locking brakes help prevent the wheels from remaining locked during hard braking. The system reduces and reapplies brake pressure so the tyres continue rolling near the limit of grip. Traction control can reduce engine power or apply braking when a driven wheel begins to spin. Stability systems compare the intended movement with the actual movement and adjust individual wheels. These systems do not create new friction. They help the vehicle use the friction already available. Tyre pressure affects the shape of the contact and the amount of deformation. Pressure that is too low allows excessive bending, heating, and wear. Pressure that is too high can reduce comfort and change the way the tread meets the road. The correct pressure depends on the tyre, vehicle, load, and use. A heavily loaded vehicle may require different pressure from an empty one. Machines contain many contacts that need opposite kinds of friction. A belt drive needs enough grip between the belt and pulleys to transfer motion. The bearings supporting those pulleys need low friction so they can rotate efficiently. A brake needs high controlled friction. The nearby wheel bearing must avoid rubbing. A clutch needs surfaces that grip when pressed together and separate cleanly when released. A screw relies on friction to remain tight. The threads press against one another and the contact resists rotation. Lubrication can make a screw easier to tighten, but it also changes how much clamping force is produced for the same turning effort. This is why important bolts use specified procedures. Applying lubricant when none was expected can create greater tension than intended. Leaving a contact dry when lubrication was required can prevent the correct load from being reached. Fasteners may also use locking materials, shaped washers, deformed threads, or pins. These features provide security beyond ordinary friction. Bearings reduce friction by replacing broad sliding contact with rolling elements or fluid films. Small balls or rollers move between the inner and outer surfaces. The contact still deforms slightly, but the resistance is much lower than direct sliding over the same distance. Bearings need suitable materials, accurate shapes, correct clearances, and clean lubrication. A tiny hard particle can damage the smooth tracks. Misalignment can concentrate the load on one region. Excessive speed can create heat. A damaged bearing may become noisy because its rolling elements pass over pits or fragments. The vibration is evidence that the contact is no longer smooth. Gears use shaped teeth to transfer force. The teeth roll and slide against one another as they meet. Lubrication reduces wear and carries heat away. The shape of the teeth controls how smoothly the force is transferred. Poor alignment causes contact near the edges, where pressure becomes high. The teeth may wear unevenly or break. A gearbox therefore depends on friction being low enough to avoid damage, but not so uncontrolled that the lubricant prevents the teeth from transferring force. The transfer mainly comes from the solid shape of the teeth. While friction influences efficiency and wear, clutches rely more directly on friction. Two rotating surfaces are pressed together. When they grip, motion passes from one part of the machine to another. During engagement, some sliding occurs. Friction converts motion into heat, while the surfaces approach the same speed. Smooth engagement requires this slipping to be controlled. Release the clutch too suddenly, and the forces can change sharply. Allow it to slip for too long, and the contact overheats and wears. Automatic systems manage similar transitions using fluid couplings, multiple friction plates, or electronic control. Conveyor systems use friction to carry materials. Packages resting on a moving belt are accelerated by static friction until they travel with the belt. If the belt is dusty or oily, packages may slip. If the surface is too sticky, objects may fail to release at the correct point. Belt material and texture are selected according to the load. Food production requires surfaces that grip products without contaminating them. Packaging equipment must handle paper, plastic, glass, and metal at high speed. Each material needs a different contact. Robots face a related challenge when grasping objects. A robotic gripper must apply enough pressure to prevent slipping, but not enough to crush or mark the object. Smooth glass, soft fruit, fabric, and metal tools all behave differently. Sensors can measure force and detect small slips. The controller then adjusts the grip. Soft pads increase the true contact area. Textured surfaces provide support. Suction may be used on flat objects. Human hands perform these adjustments almost automatically. When an object begins to slip, nerves in the skin detect vibration and changing pressure. Muscles increase the grip before the object falls. A person lifting an empty cup uses less force than when lifting a full one. The brain estimates the required grip from experience and updates it through touch. Tools are designed to work with this ability. A handle may use rubber, ridges, or a shape that prevents rotation. The size must allow the fingers to wrap around it without excessive effort. A smooth, narrow handle can require a strong squeeze, causing fatigue. A well-shaped handle transfers some load through geometry rather than friction alone. Hammers, knives, screwdrivers, and sports equipment all use this principle. The handle should remain secure during the intended force while allowing controlled repositioning. Texture can help, but sharp features create pressure and discomfort. Soft coatings increase contact but may wear. Designers balance grip, comfort, cleaning, durability, and cost. Nature manages similar balances in places that may not look mechanical. Tree roots grip soil through contact, branching, and entanglement. The root system presses against particles and grows around obstacles. Friction helps resist wind and support the tree. Wet soil can lose strength, reducing the support available to roots. Strong winds then create forces that the softened ground cannot resist. Climbing plants use tendrils, hooks, adhesive pads, and wrapping stems. A tendril coils around a support, increasing contact and using friction to prevent sliding. Some vines attach through small root-like structures. Others produce adhesive substances. The plant must gain support without spending the material required to build a thick trunk. Seeds use friction, an attachment to travel. Hooks catch in fur or clothing. Rough surfaces remain lodged in soil. Winged seeds interact with air resistance to slow their fall. Burrs inspired the development of hook and loop fasteners. One surface carries small hooks, while the other contains loops. Pressing them together creates many mechanical attachments. Pulling straight apart requires the hooks to release from many loops. Peeling from one edge removes them gradually and requires less force. This is not friction alone, but it shows how natural surfaces combine friction with shape to control attachment. Fish and marine animals manage resistance in water rather than dry friction. Their bodies are shaped to reduce drag during movement. Skin texture, mucus, scales, and flexible motion influence the flow around them. Sharks have fine surface structures that affect the water close to the skin. Engineers study such patterns for ways to reduce drag on vehicles and equipment. A reduction in fluid resistance can save significant energy when a ship or aircraft travels long distances. Small improvements become valuable when repeated continuously. Bird feathers also interact with air. Their arrangement creates lifting surfaces while allowing controlled movement. Feathers overlap, bend, and seal against one another. Friction between parts helps maintain shape, while the feather structure reduces harmful airflow through the wing. The bird needs both secure contact and flexibility. Inside living bodies, friction is tightly controlled. Joints use cartilage and fluid to allow bones to move under load. Tendons slide through surrounding tissue. The eye is protected by tears. Food moves through the digestive system with the help of moisture and muscular action. The surfaces are soft, wet, and constantly repaired. Failure of lubrication can cause pain and damage, because biological tissue is not designed for repeated dry rubbing. The mouth provides a simple example. Teeth need friction to grip and break food. The tongue and cheeks need low enough friction to move without injury. Saliva changes both contacts. Too little saliva makes swallowing difficult. Too much slippery material can make food harder to hold between the teeth. The body regulates the environment according to the task. Friction is therefore not one unwanted force that life and engineering struggle to remove. It is a resource that must be placed carefully. Feet use it to balance. Tires use it to control vehicles. Machines use it to transmit or resist motion. Animals use it to climb, crawl, grip, and feed. Plants use it to anchor and attach. Every useful contact has a range. Below that range, the object slips. Above it, energy may be wasted, materials may wear, or movement may become impossible. The best systems alternate between holding and releasing. A foot grips the ground and then lifts. A tyre grips while rolling but must not stick permanently. A clutch joins rotating parts and later separates them. A gecko attaches one toe while releasing another. Movement depends on selective friction. This becomes easy to miss because friction is almost always available. Floors support steps, hands hold cups, brakes stop wheels, screws remain in place, machines transfer motion. Remove that resistance and ordinary actions change immediately. Feet cannot push against the ground, tyres cannot steer, tools cannot remain in the hand, knots cannot tighten, nails and screws lose much of their usefulness. The result would not be a world where everything simply moved more efficiently. It would be a world where starting, stopping, holding and building became far more difficult, and even the first attempt to stand still would reveal how much grip had been doing for us. The result would not be a world where everything simply moved more efficiently. It would be a world where starting, stopping, holding and building became far more difficult, and even the first attempt to stand still would reveal how much grip had been doing for us. Imagine waking up in a world where friction between surfaces has disappeared. The mattress still supports you, gravity still pulls downward, and the objects in the room still have their usual shapes. The only change is that touching surfaces can no longer resist sliding across one another. Your first problem would arrive before you managed to leave the bed. As you tried to sit up, your hands would slide across the sheets, your elbows could not brace against the mattress, your body would move wherever the forces happened to send it, with very little control over direction. The bedding would also behave strangely. A blanket could not remain folded around you because the layers would slide freely. A pillowcase might move across the pillow with almost no resistance. The fitted sheet would depend entirely on its elastic edges and the shape of the mattress. Anything relying on fabric gripping fabric would begin to come apart. Trying to stand would be even harder. Normally your feet press backward against the floor while friction pushes you forward. Without that grip, each foot would slide away from the force you applied. Moving your legs would not provide the secure support needed to lift your body. You might try to crawl, but your knees and hands would slide as well. Pushing against a wall would send your body away from it, but stopping afterward would be difficult. You could move by pushing from fixed objects, rather like a person floating inside a spacecraft. But ordinary walking would no longer work. Standing still would require careful balance with almost no ability to correct mistakes. Your feet could support you vertically, but they could not provide sideways forces. Any slight lean would make the feet slide. The small corrections your body normally makes would become useless. A muscle would pull, a foot would move, and the movement intended to restore balance would make the situation worse. Even reaching the door would not solve much. A smooth round handle depends on friction between the hand and the surface. Your fingers squeeze inward, and friction allows that pressure to produce a turning force. Without friction, your skin would slide around the handle. A lever-shaped handle might be easier because you could push against its form. The handle would need edges or barriers that allowed force to be transferred through direct pressure rather than grip. Keys would also become difficult to use. A key can turn because the fingers hold its sides. Without friction, it would slide unless its shape trapped the fingers securely. Buttons, switches, and touch screens might still respond to direct pressure, but dragging a finger across a screen would become nearly impossible to control. The finger would move with almost no resistance and overshoot the intended position. Picking up a cup would require another strategy. Squeezing its sides would not hold it, because friction normally acts upward against gravity. The cup would slide downward through your fingers. A handle would help if the fingers could hook through it. A bowl could be lifted by supporting it from below. Objects would need rims, loops, grooves, or enclosed grips. A smooth glass with straight sides would become nearly useless unless placed inside a holder. Cutlery would need to be redesigned. A spoon could be pushed by holding its end against the palm, but a smooth narrow handle would slip between the fingers. Forks and knives would require guards or shaped grips that physically locked into the hand. Chopsticks would become an ambitious choice. Writing would also fail in its familiar form. A pencil leaves a mark because friction between the pencil core and paper removes small pieces of material. Without that resistance, the point would glide across the page without depositing graphite. Pens that release ink through a rolling ball might not work properly, because the ball depends on friction to rotate. A felt pen could still transfer liquid if pressed against paper, but controlling its movement would be difficult. The paper itself would not remain in a neat stack. Sheets would slide across one another whenever the table moved, or air passed over them. Books would be hard to hold open, and their pages would move with very little disturbance. A printed book could still contain words, but turning one page at a time would be frustrating. Fingers could not grip the edge. A page might need a hole, tab, or raised handle. Clothing would change almost immediately. Knots depend on friction between crossing sections of rope or fabric. Shoelaces would come undone as soon as tension changed. Ties, drawstrings, and many fastenings would fail. Stitches might still hold cloth together because thread passes through loops in the material, but the thread could slide through the fabric more easily. Seams would loosen unless the ends were locked with large stops or permanent bonds. Belts would not remain tight through an ordinary buckle unless the buckle trapped the material mechanically. Scarves would slide away. Rolled sleeves would unfold. Socks might move around inside shoes because fabric could not grip skin or fabric. The shoes themselves would not help you walk, but they could protect the feet from impact and temperature. They would need straps or enclosed shapes because the foot could slide inside. Furniture would refuse to stay where it was placed. A chair would move backward when you tried to sit down. Once seated, any small movement of the body could send it gliding across the room. A table would shift when touched. Drawers might slide open or closed whenever the cabinet tilted slightly. Objects placed on shelves would remain only if the shelves were perfectly level. A tiny slope would make everything drift toward one side. Pictures could not hang from simple hooks if the contact required friction. Nails and screws would lose much of their holding ability. A nail stays in wood partly because the surrounding fibres press against its sides and create friction. Without that resistance, the nail could slide out when pulled. A screw uses its helical shape to create mechanical support, but friction between the threads helps prevent it from turning loose. With no friction, vibration or load could rotate the screw more easily. Fasteners would need locks, pins, clips, or permanent deformation to remain secure. Wooden joints that rely on tight-fitting parts would loosen. Clamps could press surfaces together but could not prevent sideways movement unless they included physical barriers. Adhesives might still work because chemical bonding is not identical to ordinary sliding friction. Glue could become one of the most important materials in this world. Welding, melting, riveting, and interlocking shapes would replace many friction-dependent connections. Buildings could still exist, but construction methods would need to change. Bricks resting on one another could slide sideways. Mortar would need to bond them strongly, rather than merely fill gaps and distribute loads. Roof tiles would require secure attachments. Floorboards would need locking edges. Beams would need joints that could not move even without friction. A structure built with straight pieces simply resting together would be unstable. Every connection would need a shape that blocked motion, or a bond that joined the materials. Road transport would be transformed completely. A car engine could rotate its wheels, but the tyres could not push backward against the road. The wheels would spin without moving the vehicle forward. A parked car on a perfectly level surface might remain still until something pushed it. On a slope, it would begin moving because the tyres could not resist sliding or rolling. Brakes would fail in their usual form. Brake pads could press against discs, but without friction they could not slow the rotation. Tyres could not grip the road to stop the vehicle either. Steering would become ineffective. Turning the front wheels changes the direction of a car only because the tyres produce sideways forces against the road. Without grip, the vehicle would continue in its existing direction. Cars would need a different method of propulsion and control. They might use rails with mechanical teeth, external cables, air jets, or magnets. Ordinary roads would no longer be enough. Trains would face the same problem. Steel wheels use friction against steel rails to accelerate and brake. The grip is lower than that of rubber tyres, but it is still essential. Without it, a locomotive could spin its wheels while remaining in place. Once moving, the train could coast for a very long distance because little would resist it, but controlling that motion would require systems that physically engaged with the track. A toothed rail could allow gears on the train to push against fixed teeth. This method is already used on some steep mountain railways where ordinary wheel grip is insufficient. In a frictionless world, every railway might need something similar. Bicycles would be difficult to start and impossible to control in the usual way. Pedalling would turn the rear wheel, but the tyre could not push against the ground. The brakes would not grip the wheel rim or disc. Steering would not create the sideways forces needed for a stable turn. Even sitting on the bicycle would be awkward, because clothing would slide across the saddle, and hands would slide along the handlebars. Aircraft might seem less affected because much of their movement involves air rather than solid contact. Air resistance is a form of friction within fluids, so a completely frictionless world would have to remove that as well. Without air resistance, wings could not create lift in their usual way. Propellers and jet engines could not push air backward to move the aircraft forward. Parachutes would not slow a fall. Weather itself would change because moving air and water depend on internal resistance. The details would become much more complicated than removing grip from floors and tyres. For a useful thought experiment, it is easier to imagine that solid surface friction disappears while fluids continue behaving normally. Aircraft could then fly, but taking off and landing on wheels would still be difficult. Braking after touchdown would require reverse thrust, cables, or barriers. Boats would continue moving through water, but walking on the deck would be unsafe. Ropes could not hold knots. Anchors that depend on dragging through the seabed would be less effective unless their shape caught physically. Sailing ships would lose many familiar systems. Ropes wrap around posts and pulleys, because friction allows them to hold tension. Without grip, sails could not be controlled in the same way. Climbers would face an impossible environment. A hand on rock would slide, a shoe on a ledge could not hold. Chalk would have no effect because there would be no friction to improve. Claws and hooks might still work if they entered cracks or caught behind solid features. Climbing would become a sequence of mechanical attachments rather than controlled grip. A person could use hooks, bolts, and enclosed handles. Each point would need to carry the body through its shape. Smooth walls would be impossible to climb without suction, adhesion, or equipment that penetrated the surface. Mountains themselves would behave differently. Loose stones resting on slopes would slide more easily. Soil would lose much of its ability to hold together through grain contact. Sand piles form slopes because grains press and rub against one another. Without friction, dry sand would spread into a flatter layer. Each grain would slide until blocked by a container or another permanent obstacle. Dunes would not keep their familiar shapes. Paths on hillsides would be unstable. Gravel would flow more like a collection of hard liquid particles. Soil could still have cohesion from water, roots, clay, and chemical bonding, but friction between grains is a major part of its strength. Foundations would need to account for ground that could not resist sideways movement in the usual way. Landslides would become common wherever material rested on a slope. Rock blocks would move unless locked by shape or bonded together. At the same time, earthquakes caused by faults sticking and suddenly slipping might change. Tectonic plates would not build stress through friction in the same way. Some movements could become smoother and more continuous. The planet would not become safer overall. It would simply trade one set of geological problems for another. Machines might appear to benefit because sliding parts would no longer waste energy as heat. Bearings would become unnecessary in some places. Shafts could rotate without rubbing. Hinges would move freely. The advantage would last only until the machine needed to transfer force. Belts would slip over pulleys. Clutches could not connect rotating parts. Brakes could not stop them, screws would loosen, tools would slide out of holders, a drill bit could rotate, but it would have difficulty cutting because cutting depends on forces between the tool and material. The bit would need a shaped edge that physically pushed material aside, yet without friction, the contact and removal of chips would change greatly. A saw would not scrape wood in the familiar way. Sandpaper would polish nothing because its grains could not drag against the surface. Grinding wheels would lose their effect. Manufacturing depends on friction, both as a useful force and as a problem to control. Remove it completely and many processes stop working. Rolling bearings reduce friction, but they still need enough contact to make the balls or rollers rotate instead of sliding. With no friction, a ball touching a moving surface might not begin spinning. It could simply remain rotationally still while the surface moved beneath it. Wheels face the same problem. Rolling is useful because static friction allows the point of contact to remain briefly fixed. Without that contact force, a wheel is only a round object that can spin without pushing against anything. Energy used would fall in some moving parts, but getting energy into or out of those parts would become difficult. Power tools would need direct interlocking gears at every stage. Motors could rotate shafts, but the shafts would need keyed connections or shaped locks. Smooth press fits would fail. Every machine would become more dependent on geometry. A square shaft could turn a square socket without friction, because the flat sides push directly against one another. A pin could block a sliding piece. A toothed gear could drive another gear. These mechanisms already exist, but friction helps them remain stable, reduces rattling, and supports loads between the main contact points. Without it, clearances would produce constant movement and impacts. Machines might become noisy even though rubbing sounds disappeared. Parts would knock against barriers because nothing could settle through friction. Vibration would last much longer. A moving component normally loses energy through friction and gradually comes to rest. Without that energy loss, oscillations could continue. A door pushed open might swing back and forth for a long time if the hinge and air provided little resistance. A drawer could bounce between its end stops. A dropped object might keep sliding across the floor until it hit a wall. Rooms would need soft barriers around their edges. Sports would become nearly unrecognizable. Running would be impossible. Football players could not accelerate or change direction. The ball would roll for a very long distance unless air resistance slowed it, or it hit something. Kicking the ball would also be less controlled because the foot could not grip its surface during contact. Spin would be harder to create since spin often comes from friction between the foot and the ball. Tennis players could not move across the court, and racket strings would interact differently with the ball. Bowling balls would slide without gripping the lane, reducing their ability to curve. Gymnastics would lose most forms of support. Hands could not hold bars by squeezing them. Athletes would need handles that enclosed the wrists or fingers. Swimming might remain possible if water resistance still existed. It could become the easiest familiar form of movement, although reaching the pool would be a challenge. Daily tasks involving food would also change. A knife cuts partly because its edge presses into food, so some cutting could still occur through direct pressure. Holding the knife and keeping the food in place would be difficult. A chopping board could not grip the counter. The food would slide unless placed in a shaped holder. Jars and bottles would need handles or mechanical opening systems. Grinding pepper would fail if the grinder depended on rough surfaces crushing and dragging the peppercorns. Mills could still break material through interlocking teeth, but the design would need to prevent everything from slipping away. Chewing would be altered. Teeth use shape and pressure, but friction helps grip food and move it between the teeth. The tongue also relies on contact with food and the mouth. Swallowing depends on lubrication and muscular pressure, so it might still work, but controlling dry, solid food would become harder. Meals would favour soft foods, containers, and utensils designed to trap rather than grip. Life in nature would face enormous challenges. Animals that walk would lose traction. Hooves, paws, and pads could not push against the ground. Claws would still help on surfaces they could penetrate, but smooth rock and firm soil would provide little control. Birds could fly if air behaved normally, but taking off from a flat surface would be difficult. They might use claws to push from branches or launch by dropping from heights. Perching would depend on toes wrapping completely around a branch. Friction normally helps the grip. Without it, the feet would need to lock mechanically. Geckos use molecular attraction rather than simple rough surface friction, so some of their attachment might remain if that attraction were allowed in the thought experiment. Separating adhesion from friction is difficult because the two are closely connected. A surface that adheres usually resists sliding. If all resistance to sliding vanished, many adhesive systems would vanish with it. Insects would struggle to stand on leaves and walls. Spiders could not control movement along webs in the same way. Snakes could not push against the ground. Burrowing animals might still press against tunnel walls if their bodies physically filled the space, but loose soil would shift around them. Plants would also suffer. Roots rely on contact with soil to resist being pulled out. Friction between roots and soil particles helps anchor trees against wind. Without that resistance, roots would need to wrap around rock or bond chemically with the soil. Tall trees might topple more easily. Vines could not rely on wrapping tightly around supports unless the shape locked them in place. Seeds with hooks could still catch in fur, but smooth seeds would move easily across the ground. Pollination might change because pollen grains often cling to insects and plant surfaces through a mixture of adhesion, texture, and electrostatic effects. Removing all frictional contact would disturb those processes. Even the cells in living tissue depend on controlled attachment. Cells connect to surrounding structures and to one another. Muscles transfer force through proteins and tissues. Skin layers resist sliding. These biological connections are more complex than dry friction between blocks, and many involve chemical bonds. Still, a world where matter could not resist sliding at interfaces would threaten the mechanical structure of living organisms. Our bodies are not simply bags of parts floating independently. Tissues hold together and transfer force. Muscles pull on tendons pull on bones. Skin moves over underlying tissue but not without limits. Blood cells pass through vessels while interacting with their walls. At the smaller scales, the distinction between friction, adhesion, viscosity, and molecular bonding becomes difficult to maintain. Removing one without changing the others may not be physically possible. That is the main limitation of this imagined world. Friction is not an extra substance that can be switched off while everything else remains unchanged. It grows from electromagnetic interactions, deformation, adhesion, and the internal behavior of materials. The same atomic forces that contribute to friction also help give solids their strength. If we remove those forces completely, objects might no longer remain solid. Hands, floors, tires, and tools would not simply become slippery. Matter itself would behave differently. The useful version of the thought experiment therefore removes the resistance to sliding while leaving the rest of the world mostly familiar. It is not a possible universe described in every detail. It is a way to reveal how many ordinary activities rely on grip. The result shows that friction is not merely an obstacle to motion. It makes controlled motion possible. It allows a foot to push against the ground, a tire to steer, and a hand to hold a tool. It keeps a screw tight, a knot secure, and a chair in place. It allows brakes to remove motion, belts to transfer it, and pencils to leave marks. It also slows machines, creates heat, wears surfaces, and wastes useful energy. That combination is why friction must be managed rather than simply praised or removed. Too much friction makes movement difficult. It damages components and raises temperatures. Too little friction removes control. Walking requires strong grip beneath the foot, while joints inside the body move with very low resistance. A car needs grip at the tires and brakes, but low friction inside its bearings and engine. A bicycle needs its chain to engage the gears while the wheel hubs turn freely. A living animal needs feet that hold the ground and internal tissues that slide without injury. Useful design places friction where force must be transferred and reduces it where movement must remain smooth. This balance has shaped both nature and technology. Claws, pads, scales, hairs, tread, brakes, bearings, oils, and surface coatings are all answers to the same problem. How should two things behave when they meet? Sometimes they must hold, sometimes they must slide. Often they must hold for a moment, release, and then hold again somewhere else. That is what happens during every step. One foot grips while the body moves over it. The foot releases and swings forward. The other foot takes the load. A tire does the same thing as it rolls. Each small section meets the road, carries force, and leaves. Machine parts repeat their own versions of attachment and release. Friction gives these contacts their timing and control. The force begins in microscopic regions that cannot be seen. Surface peaks meet, materials deform, atoms approach closely, adhesive junctions form, pressure shifts across the contact. When the surfaces remain still, static friction adjusts to the required force. When they slide, junctions break and energy becomes heat. Roughness changes the contact but does not explain everything. Materials, load, speed, temperature, moisture, and lubrication decide how the grip behaves. The familiar resistance beneath a shoe is therefore the result of many small processes acting together. There is no single hook hidden inside matter, and no invisible layer of glue added whenever two objects touch. Friction is an effect produced by the contact itself. Change the surface, and the friction changes. Add water, and it changes again. Increase the load, warm the material, polish it, scratch it, or cover it with oil and a new contact appears. This is why friction can seem simple during an ordinary walk and become a major field of study inside a laboratory or engineering workshop. Scientists still investigate how surfaces behave at extremely small scales. Engineers continue developing materials that grip more reliably, wear more slowly, and operate with less wasted energy. Better tires can improve safety and reduce energy use. Better lubricants can extend the life of machines. Better artificial joints can reduce pain. Better gripping surfaces can help robots handle delicate objects. Friction is ancient, but controlling it remains modern work. The next time your shoe holds the floor, a jar lid finally turns, or a chair stays exactly where you placed it. The event may not feel remarkable, nothing dramatic appears to happen. Beneath the visible surfaces, however, countless contact points are carrying force. Materials are deforming by tiny amounts. Atoms are interacting. The grip remains only because those small effects add together. A world without them would make the simplest movement uncertain. A world with too much of them would make movement exhausting. We live between those extremes, using friction constantly without needing to notice it. By now you may be lying still, although stillness also depends on grip. Your head rests on a pillow that does not slide away. The sheets remain beneath you. The bed stays in place against the floor. Even rest is supported by friction. Wherever you are listening from, you're surrounded by surfaces quietly holding, sliding, rolling, and adjusting. Some are converting movement into heat. Others are preventing movement altogether. If this explanation helped make an ordinary force feel a little more interesting, you can leave a like and subscribe to Physics with William. It helps more listeners find these calm journeys through the science hidden inside everyday life. For the moment, there is nothing you need to test and nowhere you need to push. The floor will keep holding the furniture, the bedding will remain where it is, and the world will continue providing enough grip for tomorrow morning. Rest well, and take comfort in the fact that when it's time to stand again, the ground will push back.